scared, Josh. What happened?
Probably that you're growing and learning. Is that probably what that means?
Okay.
What are you scared about specifically?
Publicly execute.
I have no concerns. I'm not even gonna sort of entertain that as a.
Promise?
Yes, I would promise that you will not be publicly executed.
We'll study with this.
All right, so we talked about last time. Complementary statistics, right? We talked about our effect size, and this is something that's going to be pretty traditional. And with our means-based test, we're going to be talking about effect sizes in terms of qualifying the magnitude and effect of an effect. If I were to have a sample of 30 and I did not find something that sort of crossed threshold for interpretability, Lindsay, but I went through and took that sample size and I cranked it up to 150, what would likely happen to that test or that p-value?
It would go down.
It would go down, right? Even if the effect was the same thing, say we're testing a correlation of 0.15, right? If I've got a sample of 50, that's not going to pop up. That would be associated with small p-value, but if I have a sample of 500, it absolutely will, right? And so thinking about our p-values are driven in great part by the size of our sample, right? And so just because something meets that less than 0.05 level doesn't necessarily tell us anything about the actual size of the effect. And this is where effect sizes come in, right? And we can start thinking about effect sizes as just a simple ratio. We've got an observed difference over a standard deviation estimate, right? And for our independent or our single sample t-test, we only have one sample. So calculating this is pretty easy. We only have one standard deviation to work with. So we divide our observed difference by the standard deviation, and we get a difference sort of in our sample relative to whatever the reference value is in terms of standard deviation units, right? And what we can do is start interpreting that as sort of giving us an estimate of the size of the effect. Okay, so we're going to work a lot with effect sizes, and these are things that have become more routine in getting pulled into psychological science. But then what I also did too is we introduced a couple other complementary statistics, and this is pulled from the American Statistical Association, talking about some of the limitations of p-values in our inference tests and some different ways to go through and supplement those, right? And we had talked about these Shannon information values, right? And the issue with our p-values, they do tell us something specific, but they're not necessarily intuitive, right? And so what we do in psychological science is we just, by tradition, truncate anything that's less than 0.001 as less than 0.001, and that might be 0.00005, or it could be 0.0000000, right? For 50 digits until we get something, right? These are sort of widely different evidence against the adequacy of our null hypotheses. Remember, if we think about from those readings, think about our p-value as a literal index of the the compatibility of our data with the null hypothesis, right? If we've got a very, very small p-value, it's basically saying if the null hypotheses were true, these data functionally couldn't exist, essentially, all the way to, yeah, it's not super common, but it's not that bad, right? With our S values, what we're trying to do is put this in terms of flips of a hypothesized fair coin, right? If I go through and say, I'm telling Johnny I have a fair coin and I get 4 heads in a row or 5 heads in a row, 5 heads in a row, Johnny, you might be starting to question whether or not I have a fair coin, right? And so thinking about that as evidence against the null hypotheses that I have a fair coin, 5 flips, you're starting to wonder, but how convinced are you on 5 flips? Not super, maybe, right? What if I had 150 straight flips with of heads? You would say that functionally there's no way that this is a fair coin, right? Same thing, right? What we're doing with these S values is just a straight derivation from P. We're just changing around the metric into something that kind of makes a little bit more sense, okay? So we talked about that, and then we talked about our Bayes factor bound, right? Bayes factor bound, playing around with a little bit of Bayesian statistics and sort of, again, using the p-value because we have that already at our disposal. Just transforming that metric into something a little bit different that's just going to give us the probability or an upper bound probability for all our alternative hypotheses relative to the null, right? And we're talking about this in terms of a likelihood statement. We're saying the likelihood of our alternative hypotheses is at most 14 times that of the null. And that starts to become pretty compelling, right? Like, so in terms of like, do we have this or do we have this, right? I don't know if anybody's sports betting or something like that, but Olivia, if I told you, who's your team, Olivia?
I'm a runner.
The
I
Bills,
have-
awesome, that's so great to hear. So Olivia says that the Bills are 14 times more likely to beat, to win on Sunday than Pittsburgh. I'm gonna bet Colorado feeling pretty good about this, right? This who's up, right? I like your heads down. But in terms of thinking about these as odd ratios, right? Now remember the thing is that when we're talking about the limitations of our Bayesian stuff is that we need a prior, right, in order to go through and do these. And this is the kind of the Achilles heel of some Bayesian approaches. And what we can do with our Bayes factor bound is we can say, assuming before we run this test, that the alternate hypotheses and the null hypotheses are equally likely. That's what we're getting with our Bayes factor bound. In actual fact, the probability of our alternate relative to the null is probably not a coin flip. It's probably not 50-50. The likelihood of the alternate is probably considerably less than the null. And so as a consequence, what that's going to do is that's going to shift that Bayes factor bound quite a bit, right? So again, we're always interpreting that Bayes factor as the maximum, the sort of best case scenario, but recognizing that that might not be a real literal interpretation of the likelihood based on our priors, okay? And then we went through and talked about, again, with that unbelievable. With the example that we went through with the schizophrenia example and things like that, showing that if we change that prior, it changes our outcomes quite a bit. Okay, so just being aware what I want and what we'll be doing for the next couple of semesters is going through and wanting you to integrate this S value, the Bayes factor bound, to try and start to get a better sense for evidence against our null hypothesis, right? Because that's what our p-values give us. But trying to do that in a couple of different ways that's maybe forcing you to think a little bit more about sort of strength of evidence for whatever effect it is that we're trying to test, okay? And if you have questions about that, I'm sure you probably do. But with these next examples, I'm going to keep incorporating this in so you can kind of see how we, or you might start to interpret or draw some of this stuff in. Okay, so which gives us to our single sample t-test. We already did the single sample t-test. Now we're going to do one just using our statistical software. As a reminder, our formal assumptions of our single sample test. We're assuming that our outcome variable is continuous. Again, in that first assignment, had you working with some levels of measurement stuff, which seems kind of like trivial, like undergrad stat stuff. But again, thinking about your level of measurement is going to be critical to identifying what type of tests that you want to use. Anytime you want to think about like how I'm going to go through and analyze these data, very first thing you should be doing is thinking about like what are my inputs, what are my outputs, and what's the level of measurement of those. You answer those questions, and you're going to have the answer. Sort of your options for analyzing your data are going to be narrowed down by quite a bit. So for our t-tests, for all of our t-tests, we're assuming that we have some continuous outcome or something that we can at least treat as if it were continuous. In psychological science, this means that we're often treating ordinal scales as continuous, right? But with some simulation research, some methods work, if we got an ordinal scale with 5 or more values, we can probably treat that as continuous without too much of a problem, but something to think about here, okay? We also want to make sure that the observations are independent, okay? If I'm gonna run a single sample test, I wanna make sure that Mandy's scores are unrelated to Daniela's scores or unrelated to Mesa's scores. No one's looking off of anybody else. We need that independence across those observations. If we don't, we start to run into some problems with estimating our standard errors. And this is where we get into some nested designs. Thinking about, this comes up in a lot of like kid work stuff, right? If I'm working with children in classrooms, right? All the children in a common classroom would likely be more similar to one another than any two random children selected from other classrooms. We have some dependence there, and then we have to get into different models that account for that, right? So there's no way to go through the test in your data, whether your observations are independent. This is just something that you need to go through and sort of think about the methodology and how this has gone through and collected, okay? We also need to, an assumption of our t-test. We have this assumption of normality, okay? But the normality assumption here, and for all our means-based tests, is a little bit tricky. Our technical assumption here is that the distribution of sample means for the population is normal. Abby, can you tell me what the distribution of sample means? Remind me what a distribution of sample means is.
It's basically like if you took like every possible sample of a certain size, it'd be like the distribution of those
Of
samples.
those sample means, right?
Yeah,
And under what conditions do we see that the distribution of sample means start to approximate normality very quickly?
when the sample size is larger.
If I have a large sample size, yes. And what else? Sure. Anybody else help her out?
Random sample?
No, not random sample, but good guess. If the population I'm pulling from is normal, if whatever I'm measuring has a normal distribution, even if I have a small sample, the distribution of sample means will still achieve normality fairly quickly, right? Again, two conditions. If whatever I'm measuring is normally distributed, distribution of sample means will start to become normal very quickly. Or if I've got a reasonably large sample, and again, that's kind of about 30-ish. 30 is not a large sample outside of just thinking about this, but that's actually a pretty decent size for cell sizes for like an experimental type of design, right? So once we get at least some reasonable representation, our distribution of sample means will start to become normal pretty quickly, okay? So the assumption of our test is that the distribution of sample means is normal. So is there technically any assumption about the actual distribution of our observed data then with our t-tests?
Distribution should also be normal.
Maybe, right? What if I don't? Kate, what if I have a very obviously skewed distribution? Can I not run a t-test with that? I can. I can do anything. I'm sure the SPSS police isn't going to come kick in the door and take away my statistics license, right? But what if I have a skewed distribution? The distribution I'm looking at, my score, whatever have collected, does have kind of a wonky skewed distribution. Do I freak out right away? Yeah.
You're talking about like individual sample, right? Yeah, probably not, because the distribution of sample means is still probably assumed to be normal.
If I've got a reasonably sized sample, right? I've got some cushion there because technically, statistically, my assumption of normality is about the distribution of sample means, not the sample that I'm looking at. Okay, so if I'm looking at, let's say, aggression scores in a classroom of something, right? And so I'm looking at aggression scores, that's probably going to have a positive skew to that, right? But if I've got enough observations in my sample, even though my sample data is skewed, I'm probably okay to move forward with my t-test, because the assumption of my t-test is that the distribution of sample means is normal, not that my actual data is normal, right? What will happen sometimes is people will go through and say, oh, my data are not perfectly normal, therefore I went through and did a bunch of crazy ass transformations on this that now negatively impact my interpretability. You don't need to do that, okay? We're still going to go through and look at the distributions of our outcomes, right? Why might we want to look at the distribution of our outcome, even if the formal assumption is that involves distribution of sample means? Yeah.
Identify outliers?
Yeah, right. Because Kate, if I've got a small sample, and I've got some people who are hanging way out on the end, that can start to drag things around. Like, yeah, distribution of sample means might be normal, but I'm not technically working with a distribution of sample means. I'm working with this distribution. And if I've got a sample of, 20, and I've got someone who's got to score several orders of magnitude above or below the rest of them, that can start dragging things around, right? So I want to go through it and sort of be careful about that. Now, again, I've said this before. I was the other night working again with some of that census data, right? So you work with outcomes like sort of income and things along those lines, right? And you can have someone whose income is quite a bit larger than everybody else, right? And so that can really start to drag things out, right? Or if I'm working in econ and things along those lines. But if the types of things that we're using on sort of ordinal, like arbitrary scales that actually don't have any real meaning, like there's only so high I can get on an extroversion measure or a handicapping measure or a depression measure. At some point, I just kind of top out the scale, right? So it tends to be less of an issue for us, but we still want to go through and take a look at that to make sure we don't have anything dragging our means around. Other thing too is we want to go through is make sure, because sometimes those scores might be quite high because someone's just really high, but maybe it's a transcription error. Maybe Johnny made a mistake when he's entering data and sort of put in a value that actually doesn't exist, right? So I want to make sure that I sort of catch that. Johnny doesn't do that, but let's say he did, right? Or it might be someone who's not a part of our sample, right? Or not a part of our intended population. So we still want to go through, we want to take a look, and it's going to give us an understanding of our data, right? Before any of you walk into a thesis meeting or a dissertation meeting or anything like that, there's no question that someone should be able to ask you about your data because you should know that back to front, right? You've gone through, you've done your screenings, things along those lines. And the approach I want you to take as we're going through and working on these screenings is thinking about setting yourself in a consultation role. Some of you may go on to do data analytic types of stuff, right? Psychologists are pretty good at those types of positions, right? And so wanting to think about if someone were to say, hey, I'm like, hey, Gabe, I want to do a single sample t-test. Here's the data. Tell me what's up with this. What you're going to want to do is pretend as though you're the consultant on that. You're walking through your bag. Well, we've got this. You want to keep an eye on this. This looks a little bit wonky, but I think it's going to be okay. Overall, here's what we can go through and do. Like you're going through and providing basically an assessment of what are my assumptions? Can we go ahead and move forward with this? How do we go through and sort of look at this data? It's going to give you a good sense for what's going on with your scores. And then also, if this is a line of research that's sort of consistent with sort of your interests and things along those lines, you start learning a lot about kind of what happens if I give people these measures or have people go through this paradigm. Like I thought that people were going to be really high on this, but they actually weren't. Or I didn't know people were going to respond to this, but they've actually looks like they've kind of floored out or ceilinged up, right? Lots and lots of information that you're gathering from the screening process, okay? So you can approach it as these are the steps I go through and these are the things that I say, but if you're taking that approach, you kind of miss the point and it'll be really irritating to do that and feel like just writing your name on a chalkboard over and over again. What I want you to be doing is think about like what's going on in these data and what's the connection between sort of the constructs that we're wanting to measure and the actual observables that we're getting. How are those two linked together? Okay. So, getting back, there was a little bit of a digression, but thinking about our single sample test, again, main thing we want to make sure is that our outcome variable is continuous and recognizing that we have an assumption of the distribution of samples. Okay. We also have some informal assumptions that our data don't contain extreme values, right? This isn't a formal assumption, but again, we want to make sure that there's no one popping up that's really dragging our means around one way or the other, okay? And then the other thing too is all of our auxiliary hypotheses. We talked about this before. These aren't things that are statistically sort of embedded in them, like, oh, you need to do this, but all of our statistical theory and sort of the assumption of these distributions is predicated on the assumption that our sample is representative, that our sample is random, that we don't have violations of distributional assumptions, that we generate our hypotheses before we analyze the data. I have a correctly specified model. That means everything that's in there needs to be in there, and the things that don't need to be in there aren't, right? I've included all relevant variables. My measures are valid. my measurements are collected without error. We obviously always violate those things, right? Because it's applied statistics, but just because we violate them all the time, we need to be aware that these are all auxiliary hypotheses that kind of go into, in a vacuum, this is when these models work. Now we can start to tolerate some violations, but as things start to compound and compound and compound, we need to be aware of the potential impact that has on our inference, okay? And taking that into account when we're making our interpretations. Questions about this? Yeah, ready.
So we need to be as careful as possible to not violate this list, but then we will.
Yeah. I mean, because our samples are probably likely very rarely going to be completely representative of. We all do research wanting to infer something about human beings, right? But I'm guessing that few of us, I don't know, even something like, I'm gonna pick on you, Mesa, so sort of in Cynthia's lab doing stuff with ADHD and emerging adults and college students, right? So there, college students are an appropriate group, right? Because but are University of Wyoming students representative of all college students in the entire country? No, they're absolutely not, right? Does that mean you shouldn't do research with the students at the University of Wyoming? No, but what we probably ought to be doing is thinking about what happens, who's the population I'm trying to generalize to? Who did I get? And is there a mismatch there? And so what are the potential implications? If I were to get this, so here's what I found, but if I were to look at that in a truly representative sample, would I expect things to change, right? Maybe I would, maybe I wouldn't, but that's kind of the thing we want to be thinking about, right? And like none of our samples are randomly selected samples. We can randomly assign people to groups, but we can't randomly select undergrads, right? We have to have people coming in. Now, does that self-selection impact what I'm looking at? Maybe, maybe not. That's a question for you to ask, right? Same thing with, is my model correctly specified, or things that I would need to have in there and things that are not. If I'm looking at a sort of 2-sample t-test, like there's probably nothing in psychology that's determined by one grouping factor, right? So there are probably other things that determine sort of differences across sort of these groups, but I want to be thinking about, okay, what are the compounds, what are the alternative explanations that start to come in, and I start to sort of put this together, right? So again, these are all things that are assumed by the analyses, right? These are never all true, so it's up to us to start thinking about what are the implications, and that's where that limitations and future corrections section really start to come in. Yeah.
I think you answered my question. I was gonna say, and this is like the parts we mentioned in like our discussions and like the future
Yeah.
research
Yeah.
of the ones we are aware of.
Yeah. And so again, it's a thought experiment, right? Like if I were to, this is at least how I approach it, right? Okay, so I do work at the University of Wyoming, where 80% of my sample is going to identify as white non-Hispanic, right? That's clearly not representative of people, right? If I were to go through and get a more diverse sample, right? I can't, because I'm where I'm at. I only have so the tools that I can work with. But if I were to do that, would I expect my effects to change? Would things strengthen? Would things weaken? Would things still show up, right? And based on research on sort of whatever I'm looking at, I'm like, well, if I'm looking at like some of the stuff that we do in the lab, thinking about like beliefs and sort of how people interact with people and sort of social dynamics and things like that. Like, I don't know that the social dynamics of Wyoming undergraduates are representative of all people in the United States. So what would happen if I were to go through and do that, right? So just using this as kind of a basis for thinking conceptually about limitations to our research, how things might look at, because it's easy to just say, oh, I should have a more diverse sample. Well, sure, you should. But just saying that as a stock phrase is kind of lazy and doesn't actually do service to thinking about getting more diverse research, because I haven't actually thought about it. I just like threw that out there as kind of an easy thing to say, right? Well, fine. Yeah, I agree. But what also happens? Like, so what about my effects and my interpretations might not hold or carry or generalize if we were to go through and use a more representative sample or a truly randomized sample. Is there something about self-selection that might come in if I was doing something looking at self-handicapping or something like that, right? If you're sort of doing self-handicapping stuff in Sean's, like there might be something different about students who sort of get on the ball and volunteer for research early on in the semester that makes them a little bit different than the folks who just didn't do their research. I might be capturing a different subset of the population, right? And so thinking about what goes on in the potential impacts of our research. Sometimes it'll make a difference. Sometimes I might say, well, maybe it doesn't make a difference. I don't know. But that's the things you should be thinking about that are separate and different from, there's no statistical test. I can't test whether or not this generalizes. I can't test whether or not that I had a random sample or not makes a difference. That's where you want to be going through and thinking about impacts, and that's where you have to use a little extra brain power with that. Okay. All right. So going to use our actual example here. So what we've got inventory, the inventory of interpersonal processes or problems 32, self-report measure intended to assess domains of interpersonal difficulty. Total scores range from 0 to 128 with a mean of 25 in a representative validation sample of 800 adults. And so here are our demographic variables of our nationally representative sample here. Okay, researchers are interested in the effect of stress exposure on global interpersonal functioning. Responses to the IAP 32 were obtained from university undergraduates reporting to stress associated with exposure to prior trauma. Okay, so here we've got characteristics of our sample. Okay, so what we want to do is we want to go through state the null, in a sense, state the null hypotheses tested, state the null and alternative hypotheses using symbols. I want to calculate a 95% confidence interval for interpersonal difficulties as measured by our assessment for this sample, right? We're going to provide an index of the absolute magnitude of the difference in the sample relative to the normal population. What are we talking about there? What are we calculating? Yeah, you got it. What is it, Olivia?
Effect size.
It's my effect size. It's a magnitude of the difference. This is how we're eating lips. So relative to the normal population, you're going to conduct a hypothesis test at 0.05, report and interpret an S value, report and interpret a phase factor bound, and then summarize conclusions, kind of pull this all together. Okay. So what we're going to do is if you open up your SPSS set, okay. This is our data set here. And I'm going to go through and pull up my single sample T screening handout here. Sure, everything. Okay. So what we're going to do is just a couple of quick, and we're going to have lots of opportunities to screen data. So we're not going to sort of step-by-step walk through this. We'll walk through in SPSS, the independent samples T example. But first thing here, what we're going to do is we've got our participant number, we've got sex here, age, ethnicity, and then we've got different subscales for our IAP. And then our IAP total. This is the variable we're going to use. And so if you go through, I've set these handouts up to be a very practical guide for all of these that we're going through. You should be able to walk through these using that sheet and be able to reproduce everything that we're doing here. We'll see for this question, basically what we've got is we have average IAP scores for a nationally representative population. Our question is boy, does trauma exposure maybe impact people's interpersonal functioning? And so what we're going to do is we're going to conduct an independent sample t-test, or excuse me, a single sample t-test to compare our sample of trauma exposed undergraduates against the normative population. Okay. And so we've got a reference point here. So all we're concerned about with our single sample test, we've got our ID number that just tells us who's who. We've got our total score here ranging from 0 to 128. And then we're testing this against a reference value of 25, right? We would expect, if we are not seeing any different, that our undergraduates who've been exposed to trauma should have a score somewhere right around 25. If they don't, suggest that maybe our experimental population, our trauma exposed undergraduates, may have a level of interpersonal functioning that's not identical to sort of our nationally representative sample, what we'd expect there. Okay. So what we're going to do first here is, because IAP is our outcome, this is our dependent variable here. What I'm going to do is I'm going to click on IAP total, and I'm going to right click, and then I'm going to go down to sort ascending. This is just a shortcut. I mean, you can go to data, sort cases, and sort of walk your way through all that stuff, but we don't need to. So you just go through, right click, sort ascending, and we'll see that we've got 70 cases where we're missing data, right? Now, if I'm missing data, I can't use those cases. Those are cases that are just gone because I don't have scores for them, right? But this is something I'm going to want to take note of, because that's, I mean, I had a big sample, but I'm missing a lot of folks here, okay? Other thing too, everybody look at me in the eyes. Anytime you have a data set that you're working on now, here it doesn't matter because I've got copies, but with your own data, have a file that's just the data, the original, that you set away and don't touch, right? That's an archive file. Have a working set that you go through and are using, because otherwise what's going to happen is you start jacking around your original data set, and then you save it, and then there's no way to go back through and get your other stuff. So anytime you open up a set, always go through and save as a scrap file or a working file or something along those lines, so that you've got that sort of original set retained, right? So what I'm going to do here is I'm going to go file, save as, and for me, if it's just a set I don't care about, I just name it scrap, because anything that's named scrap, I know that I don't care about, and I can just keep saving over and over and over it, okay? So what I'm going to do now is, because I know that these aren't cases that I can use, I'm just going to go up. I'm just going to get rid of them. Okay. But I'm going to go down through, take a look at my IIP, and again, if I'm looking at my sheet, I know that I range from 0 to 128 with this. And so if I go down through and take a look at my scores, boy, we've got a case here, 335 with a score of 999. Okay. Is that a reasonable score for this? Nope, it's not, right? So again, I'm going to start going through, anytime you're going through and running these screenings, you should add a sheet of paper, sort of an open document or something like that, where you just started to write down, like, what are the things that I'm finding, right? So we know that we've got 70 scores that we're just missing data, and we need to account for those somehow, right? We also see that we've got a case that doesn't have a plausible value. It's 999. Now, I don't know if someone miskeyed that and just hit an extra 9. So maybe that's 99. I don't know. Or what I will do in my research is often, like, if there's like an actual missing value, right? I'll type in a 999 because that's rarely a plausible score for anything. And that signifies that that score is actually missing. Someone's looked at it and verified that, yes, that score isn't there, as opposed to a blank value. I don't know if it's actually not there. Someone just forgot to enter it or something like that. This is a deliberate code that tells me it's missing, but it's a little bit ambiguous because I don't know if this is just a miskey, because I just deleted a bunch of scores, cases with missing values that just didn't have anything. This could be a 99, an actual 99 score. It could be a missing value. I don't know. Doesn't really matter because I don't have a basis for going through and taking a look at it and figuring it out right now. So what I'm going to do is identify case number 414 as having an out of bounds value. And I'm going to go through and get rid of that one too. Okay. So if we go through and take a look in terms of our screening, and don't worry about this. I'm just using this to save some space. We'll go through a full screen with the independent sample sheet. You'll see how to go through and do all this. But what we're gonna do is, first, we're gonna go through and request descriptives for indices of skew and kurtosis, and we're gonna save some Z values, okay? Skew and kurtosis is gonna give us a sense for if our data are approximating normality. Saving our Z scores, that's gonna give us an opportunity to go through and take a look at whether or not qualifying or quantifying the extent to which we have outlying values, okay? What I'm gonna do here is I'm just requesting a histogram of my IIP total scores here, requesting a box and whisker plot. And then here, what we're doing is using this identify individual outliers, okay? So if I go through and I take a look at my descriptive statistics here, people can see what am I, someone tell me something, what are you seeing in terms of this line of descriptives? What do you think, Haley? How's our sample size look?
That looks good.
Outstanding, yeah, I'm super jazzed about that, okay? What about my minimum, my maximum statistic?
That looks fine.
Yeah, everything's in balance, right? Looks like I got a mean. Already, what's the mean we're testing against?
Like the 39.8.
Yeah, what's our mean under the null? What's our reference value?
Oh, 25.
25, so already, I'm starting to guess, boy, I don't know, I haven't run my test yet, but with that sample and that far above the mean, it's looking like maybe our trauma exposed undergraduates might sort of be reporting higher levels of interpersonal difficulties than what we would expect out of the normal population. Don't know yet, but all of a sudden I'm just sort of thinking and noticing, does this make sense, right? Always thinking about, do my data, what I'm seeing, does this make sense? Credibility is a big thing, okay? Standard deviation looks like we have some variability. What about our skew and kurtosis values here?
Kurtosis is the statistic is pretty like
Okay.
close to 1 negative.
So we've got some negative kurtosis there, right? Which suggests kind of maybe a more boxy type of distribution. Is it something we should get too worried about?
No.
Probably not, right? What about our skew?
It looks okay. It's only
Yeah.
0.1. Yeah.
That's 1.19, right? Again, not too bad. Remember, our rule of thumb is skew kurtosis less than 2. It's kind of a rough, so like now, that's not to say that anything that ekes above my skew is 1.98, that it's fine, and if it's 2.01, that it's unreasonable, right? But it's just saying, basically here, and I think I want to sort of really impress upon you what we would say in terms of language, saying like, here we're not seeing problematic deviations from normality. Are our data perfectly normal? No. But it's rare that we're never gonna get perfectly normal data. What we're looking for is there something about these data that would cause us some concern in terms of our underlying assumptions, okay? Yeah, Andy.
So like, did you say like skewed kurtosis, like less than 1 is okay?
Well, this is what I understand your question, Andy, but I dislike it immensely. No, this is the thing, and sort of like everything else, like what we want to do is we want to fall back on hard and fast rules, right? Like if it's this level, then it's fine. If it's not, then it's not. Like this sort of distinction, sort of yes, no thing. Please don't approach any of this stuff in that way. We're going to give you like general guidelines that are just commonly used so that you're aware that this is kind of how people talk about things, but it all really depends on context, right? Because one of the things, Jim, remind me what's our normality assumption with this test?
Then it's normal.
It's normal. What's normal?
Yeah.
Yeah. Which one of the distributions though? Okay. Close. The distribution of, I guess we link it together. The distribution of sample means, right? And under what two conditions do we know that the distribution of sample means starts becoming normal very quickly?
Got it this time.
You got it.
Okay, so the increased sample size or
Yeah.
larger sample size and that. Oh, maybe I forgot the second one, dang it.
The population
Yeah.
is normal.
Yes, thank you.
Lucy, I don't know if population distribution is normal on that, but I would imagine kind of, right? Some people are gonna have no low levels, some people are gonna have high levels. But why does it not matter in this case? What the population distribution looks like? So, yeah, what about my sample makes me not worry about whether or not the population distribution is normal?
Bigger.
Yeah, it's massive, right? At 330 some cases, this could have a really wicked skew and it doesn't matter because the distribution of sample means is still gonna be normal at that level, right? And so Mandy, this is why I'm saying, so like, oh, what's my rule of thumb of what's problematic and what's not? It all depends on other stuff, right? Here we've got a really, really large sample, right? So the actual distribution of this probably isn't gonna make too much of a difference. I wanna look at what it is, right? But that large sample is really buffering me from a lot of stuff.
Okay.
Yeah.
So, if the sample size is normal or is big. And the population size is normal,
The distribution is normal, yes.
sorry, the distribution
Of the mean.
of the mean, thank you, is normal, then we don't have to worry about the skewness, cause that will like make us be okay if we fall.
Maybe, it depends, okay? So again, I see what you're trying to do, resist this urge. To sort of try and come up with, because there's just several different decision points, right? So like wanting to think about like what's going on in these data. So, and sort of, it should always be, am I concerned about this or not? Okay, now with this situation, skew and kurtosis, well within bounds, even if this was a smaller sample, would have no concern with this, right? Abby?
Could you review again, like what a negative means in terms of like a kurtosis statistic?
Negative kurtosis is that platypus, right? This is your platypus. And sort of going back to old school student stuff. Positive kurtosis, this is gonna be like your T distribution. It's kind of a more peaked than some flat tails, right? You kangaroos, exactly.
And
right?
so, and then, so then with like skewness, like a negative statistic would literally mean like negative skew.
Negative skew.
Okay, got it, thank you.
Positive skew, okay? And so this is what we've gone through, and we've gone through and taken a look at our descriptive statistics. This is all looking good. And then when we go through and pull up our histogram. Johnny, what is this histogram looking like to you? Yeah, or maybe not normally, but it's at least kind of symmetrical, right? It's kind of boxy, right? We saw that has some negative skew in it. It's just kind of, it doesn't have like sort of those really nice tails, but there's nothing in there that's sort of overly concerning or problematic with this, right? What's maybe the one thing you're seeing maybe on that right side of that graph?
99.
Yeah, we've got like a case that's falling a small ways away from the rest of the distribution. It looks like there's maybe a case or a set of cases that are a little bit high. They're not super far out. They're not, I mean, I might note that they're sort of kind of detached. But again, this is the tricky thing with histograms is if you all run this in SPSS and John, you run this in Stata, the graph is going to look different because the shape of this graph is all based on the bins and stuff like that. So histograms are a very nice tool, but we can start jacking around with them and sort of making them look different depending on how we go through and bin things, right? So what we're going to do then is we're going to go through and I'm going to have you look at your box plots as well. Someone go through, Daniela, can you tell me, what are you seeing with this box plot?
Score, the max score. We see the first quintile, the third quintile. We see the mean. And
Beautiful.
the,
What's this line represent? Is it the mean? The median value.
Okay, yeah, it's a box plot, not a normal.
Yeah.
Okay.
No. So just make sure because these are median based statistics in this. And the nice thing about the box plot, there are rules for building your box plot, right? So the box plot that you get in Stata is going to have all the same stuff as the box plot as in SPSS. So that's sort of more consistent, right? And so if we're going through, so we've got Danielle, how do I know that this is the minimum value and that's the maximum value?
From the numbers, no?
Okay, what features of this plot tell me that those are the minimum and the maximum?
That things,
What's that now?
that bracket thing?
Yeah, so the whiskers,
Oh, the
do
whiskers.
the whiskers always indicate minimum max values in these box plots? No, sometimes what I'll have is I'll have values that are extended beyond 1.5 times the inner quartile range. I'll have sort of plots above or below, but you're exactly right. In this case, that represents the minimum, that represents the maximum. There's no one sort of really hanging out and being sort of more extreme than 1.5 times the inner quartile range.
If it wasn't, would it just be a dot? Is that
Yeah,
what it is?
just a
Okay.
dot.
Asterisk.
What's that?
Just saying, they were like asterisk. I remember
Yeah,
the example.
so, and so the different programs do it a little bit different. SPSS will have open dots for things that are falling outside 1.5 the inner quartile range. If things go beyond 3 times the inner quartile range, they'll turn into asterisks. Stata won't do that. So you just have to kind of be aware of sort of how those are put together. Yeah.
This is probably a dumb question.
No.
For the problem sets,
Mhm.
we're doing this on the computer.
Yep.
We're not like doing it by hand.
No.
Okay, all right.
This is all sort of generated with the computer.
Okay.
Yeah. It could be a desktop, which will be a struggle for you. It works the same way.
This might be a specific question that
Yeah.
maybe I can circle up if you have another time. With the stata single sample, I'm having a tough time figuring out how to drop those observations.
Okay, yeah.
Okay.
You'll catch up with me. I'll go through and show you how to do that. Yeah. It won't matter for this. You can still do it and because they're not there, so it's not gonna include them anyway. So don't worry about that.
You can't drop the 999.
What's that?
You also can't drop the 999 then?
Oh, that's true.
And I just can't see it on the PDF.
What's that? Do you have the data set open?
Yes, I do.
Open up the data.
This reminds me, because we made these slides and I just did not call them.
Okay, yeah, that's your spreadsheet. Just highlight stuff.
Anything else?
Cool, no worries. All right, so here with, yeah.
Alright, so you were saying that, if this doesn't have the whiskers and it has like the asterisks.
Well, it'll always have the whiskers. The whiskers are part of it. If we have points outside of those whiskers, those are telling me that I have values that are more than 1.5 times the inner quartile range. Remember, inner quartile range, this is your middle 50. This is like your middle 50% scores. If I have 1.5 again outside of that, then I'm going to go through and sort of start to have points come up. My whiskers, the ends of my whiskers here, they're either they're one of two, they indicate one of two things, either the min or the max, or the most extreme value that still falls within 1.5 times the inner quartile range.
So we could still have like values past the
Mhm.
upper bound,
Yep.
and that's where you'd show the asterisks.
Yeah, then we'd see like sort of open dots and asterisks. And you'll see these will come up in the next example. Yeah, Kate.
I was just gonna say, if like, we had somebody who, one person that got 128 or something like that, they would probably show up.
Yeah, if we had someone sort of go through
Like
that,
the
that would
top end.
probably pop up there. Yeah, Jen.
For this measure, does higher score mean like more trauma?
Yeah,
Okay.
more difficult.
interpersonal.
Okay.
More in-person problem, but thank you for asking that because this is important. Like I go through with these examples and try and give you enough information sort of to make interpretive value, like sort of what do higher values and lower values mean. Always want to know before you jump into this, like what those the temptation will be to just like jump right into the data and start like punching out stuff. Resist that. Make sure that you have a good, even if you have to like take some notes, understand exactly what these data are looking at and how they were developed. It's going to save you time as opposed to kind of feeling like you're wandering around in the desert trying to figure out what's up. When you just have a good conceptualization of what we're measuring before you jump in there. So yeah, that's an excellent question. Okay. So here with our box plot, we're saying, all right, so we've got a min and a max. It's not perfectly symmetrical, but it's not looking too bad. There's really nothing too much going on with this that would cause us any concern. Okay. So at this point, last thing we're gonna do is we're gonna drop down and we're gonna look at our descriptive statistics here. What SPSS is doing when you run the descriptives on the front end is it's just gonna calculate Z-scores for everybody in your sample, okay? Which is why you wanna go through and drop cases that you don't want in there before, because otherwise it's gonna change your Z-scores, right? But if we go through, it's gonna run Z-scores, and then we go down through and just run some descriptives on our Z-scores. Gabe, what are you seeing here in sort of this, the descriptive statistics for our Z-scores?
They're pretty like small, I guess. Like,
Okay, what do you mean by small?
wait, I can't see. Wait,
Okay.
sorry. No, you're good. You're good.
No, I'm give you every opportunity to succeed, man. That's my job. So what do we want to focus most on this table if we're looking at Z-scores? Why are we requesting Z-scores in the first place? Standardized what? Standardized scores in the service of comparison with what?
I was gonna say with population, but that's better.
Okay. We don't have population information, right? So we can't sort of necessarily sort of fall back to some of the stuff that we were doing before, right? What are Z-scores helping us do in this screening? If I want to know how far out a score is, if I say, hey, this score is far out, and I just say, Olivia, hey, I got some data with some far out scores, right? I don't know if you, that doesn't mean anything to you, right? Like, I don't know what that means, what you mean by far out, right? So like, what we can start to do though, if I say, hey, Olivia, I've got a Z-score or a score that's registering with a Z value of 3.6. What does that tell you about that score?
It's kind of high.
It's pretty high, right? It's specifically, it's 3.6 standard deviation units from the mean, right? And so that's pretty high. Here, we've got our low score, our lowest score in the distribution is about 2 standard deviations from the mean. Here, our upper is about 3 standard deviations, right? We haven't talked a whole lot about this, but again, if we're thinking about, again, rough estimates, right? Thinking about Z-scores corresponding to p-values. Z-score for p equals 0.001 is 3.29, right? We've got stuff that's, and again, when we've got a really big sample, as my sample size gets bigger and bigger, am I expecting it to capture some more extreme scores? Yep, I for sure am. That's, if I don't, I'm kind of worried that I haven't actually gotten a good representative sample, right? But even if I do have really large or samples that are falling quite a ways from the mean, am I worried about it in this situation? Saying no, Jalen, why not?
Oh, I just started shaking my head.
That's all right, but your gut, your gut was telling you right. So like would I be concerned? So I've got something that's about 3 standard deviations above, 2 standard deviations below. If we went back up and we look, we see, okay, we've got a couple scores cases here falling away from the mean. Am I worried about these values? Probably not. And why not?
They're not too like
They're not too bad.
crazy,
They're
and it's
not
not
too
where the bulk of everything's going on.
Right.
Just doing their thing.
Okay. What's the thing about this sample that makes me not worry about that at all?
It's a large sample.
The large sample, right? If I were to have a sample of 15 and have these Z-scores, then maybe I'd be a little bit more concerned if there's sort of folks getting drug out there, right? But again, large samples, it gives you a lot of cover for a lot of stuff, right? Any single individual observation in this is not going to have that big of an impact. And we'll talk about this when we get into regression. If your entire model starts changing because you pull out 1 or 2 people, that's a bad thing. That suggests that something's not stable in there, right? With this, I should be able to drop any handful of stuff, put it back in. It shouldn't change things in a meaningful way. Yeah.
I know you don't want us to develop like dichotomous rules.
Yeah.
But I wanna ask a hypothetical just to
Sure.
make sure I'm like fully grasping this.
Yeah.
So like our kind of assumption is that like 30 would be an adequate sample size. If this sample was 30 and we saw like a score that was 3 standard deviations above the mean, are we concerned then?
No, probably not if that's what the distribution looks like. Everything's kind of boxed in. We've got a reasonable spread,
Okay.
right? I mean, it's not too bad.
Okay.
If everything's stacked up at 0, and then we've got one person like 3 standard deviations above the mean, now all of a sudden I'm wondering about the representativeness of that observation, whether or not I have some problems with that. Yeah, maybe.
Can you go into the box?
Yeah.
So I'm just trying to remember, like, I think I saw this in the book. So based on the shape of this, we can see that it's slightly right skewed,
Yep.
right? If we were to turn it sideways.
Yep, a little bit of positive skew, a little bit,
Positive
not
skew.
too bad.
Okay.
Yeah.
That's it.
Okay,
I just
yep.
wanted to like.
Yep,
double
yep.
check on that.
And so this is the thing, like these different things, with each one of these, I'm gonna have you look at your skew and kurtosis. I'm gonna have you look at a histogram. I'm gonna have you look at a box plot and interpret these things. I'm gonna have you look at z-scores, right? But each step by the time you get to the end, like, there shouldn't be anything that's coming at you like out of nowhere. You're like, oh, wow, that's, like, after you look at those skew and kurtosis values, you should have a reasonably good idea what that histogram is gonna look like. And if you look at the histogram, that's probably gonna give you a reasonable understanding of what to expect from that box plot. And by the time you get to the z-scores, you should have a reasonable understanding of kind of what might be going up. It's just giving you different looks at data so you can go through and help you sort of contextualize what's happening and then be able to describe it to somebody else. Again, with this, think about putting on your consultation hat. Some of you may end up being statistical consultants, right? Where you're going through and helping people go through and run this type of stuff. Being able to sort of describe things in language that other people can understand, communicate so that people can follow through and replicate whatever you've done is going to be critical for success in that type of thing. And then even if you're not a statistical consultant, if you're doing any type of research in collaboration with other people, boy, it's nice if you can have someone sort of tell you something and explain it in a way that I get a good handle on what it means as opposed to, Christ, I don't know, even if you did, let me see, like, I don't understand words or right? So going through and sort of putting together things in a format so that you can communicate things to other people. So if we go down through and take a look at sort of the end of this handout, just have a quick single sample screening summary here. Again, you've got handouts. Don't get creative. This is not a time for you to express sort of anything that's unique about you. This is something I very much want you to follow in terms of going through this format. It's just a nice way to go through that. Once you get out on your own, you can do whatever you want, right? But for this class, just trying to give you some structure and a way to go through and talk about things, right? So always with the screen, we're going to start with missing values. How many scores are missing? Well, here we've got missing values for 70 cases. Want to make sure that we have documented that. Accuracy, plausibility, we've got 1 invalid score. And here I'm telling whoever's reading this exactly what that score is for case number 414. Okay, these are the things we've found. We've gone through cases with missing and implausible values removed. This is what we have for the reduced set. Okay, so I'm just walking people through what I've got going on. Okay, then what we want to do is talk about our univariate distributions. The univariate distribution skew 0.19, kurtosis negative 0.61. Fail to indicate problematic deviations from normality. I'm not saying that the data are normal because they're not, but it's not problematic. It's not anything I'm going to worry about with this. Other thing too, two decimals are fine for skew and kurtosis. Please do not give me a skew and kurtosis value with 50 that goes to 15 decimal places. It's not a useful thing. Okay, arguably 2 is even excessive. Used to, and don't sort of cut and paste itself in there. It just kind of mucks things up, okay? We say histogram is symmetrical with one case falling slightly away from continuous distribution, box plot unremarkable, no values fall behind it beyond 1.5 times interquartile range. Do not just call everything unremarkable. What happens is people say like it's unremarkable, it's unremarkable. and I'm gonna flag it. I'm like, I think there's remarkable things about this, or at least things that you ought to comment on. So if it truly is, then you can go through and you just don't overuse that. Univariate, or extreme values data fail to provide strong evidence of univariate outliers. Here we're saying all Z less than or equal to absolute value of 2.94, right? We always want to be thinking about extreme values. They can happen in the negative, they can happen in the positive. We're just saying here, so the highest Z score we got was positive 2.94. If it was negative 3.01, I would put absolute value negative 3.01, just so that inequality makes some sense. Yeah, Jalen.
Instead of putting unremarkable, could we put something like appears normal or
Yeah,
something?
yeah.
Okay.
I mean, I probably wouldn't use, you could use normal, yeah, so it is kind of is approximately normal, or so like, this is one of the things. You'll find that it's difficult to describe distributions just because you don't have the language for it so much right now. But we're gonna do a lot of these, right? And so we'll help you build some of that vocabulary. So just thinking about things like skew, symmetry, bimodal, sort of values falling above or below or away from different stuff, just different ways to go through and describe just literally what you're saying. Okay. For these, if you want, in your screen write-ups, you can drop in, like you can take, dropping in like screenshots and just dropping things in is a perfectly fine way to do things. Do not send me all of your output, because I do not want to see that. What I want to see is that you can go through and sort of know what is important to go through and report and drop that stuff in there. But sometimes if you're like, boy, it's kind of wonky distribution, and you drop in sort of maybe a screenshot of your histogram or something like that, just so it kind of sort of follows along. That's an okay thing to do. Yeah.
I have just a general question about like cleaning data sets for when we start doing like the homework assignments. Like we would check like all the variables that are in there to make sure they're like plausible values, right? Or just,
Nope, if you're not looking at it, you don't need to worry about it. That's just stuff in there.
Okay.
What I do want you to do though, when we go through and start with these assignments is you're gonna be, what in the stuff that you're sending to Matt and I, you're gonna have, your, problem set, right? Your sort of written up stuff. You're going to have a data set and then a syntax file. And the idea is that I should be able to, Matt or I should be able to run that syntax file on the data set that you give us and replicate whatever you're reporting in the thing. That way we can go through and figure out if something's gone off, that's a documentation so that Matt and I can go through and say, looks like you did this, or you ran Z scores before you got rid of cases that you didn't want in. If you running Z scores on cases that eventually kicked out, it's going to shift everything around, right? So you want to have a clean data set and a clean syntax file. For you, it's just good habit to get into, but then also for us to go through and double check stuff.
okay, that makes sense.
All right. Cool. All right.
I have one more question.
Yes.
Okay, sorry. And this might be jumping ahead of what we need to think about right now, but like for other variables that might, not to say they're less important, but like, let's say you were looking at like gender or age or something, you wouldn't necessarily delete missing values from that, would you?
No, I don't. The only
It's more
thing-
like the outcome.
Yeah, the only thing you're gonna, I mean, those are fine variables to look at if you want to, you don't need to. I'm not gonna like give you some stuff and like, oh, the secret password is you, we're supposed to look at neuroticism and then the whole thing comes together, right? So don't worry about that.
Okay.
But this is kind of the fact that when we're doing applied analyses, sometimes there's other variables we're not using at the moment, and that's a fine thing. I can just ignore those and know which ones to go through and pick through.
Okay.
All right, so what we're gonna do is finally, we're gonna finish up with recommendations, okay? Recommendation, this is you as the consultant telling your team, your whoever's contracting with you, what's going on. We're saying, okay, we've got substantial missingness noted in this data with over 17% of cases missing total scores.
Missingness,
What's up?
missingness, is that the technical term?
Yeah.
Oh. It sounds like grammatically incorrect, is why I'm asking.
Well, that's right on.
Okay.
Never question my grammar.
Well.
Yeah, no, missingness is, we're talking about missingness in data, is, yeah, that's how we would describe sort of missing data in that is you can question my spelling. That's just, you got spell it right there. Spell anything, it's embarrassing, but no, that's correct. So Substantial missingness in the data, over 17% of cases missing sort of our outcome, right? If this is the set I've got, the fact that I'm missing close to 20% of the data is something we want to account for, right? Invalid score for case 414 is a marker for likelihood is a marker for missing value. But what I'm going to recommend is we go through, check the hard copy, like pull that case, take a look, see what was going on with that to make sure that it wasn't sort of just a miscued score and little evidence of outliers or problematic violations of normality. So missingness in the data is concerning given the potential for systematic bias in subsequent analysis, right? However, assuming there's a justification for that, we recommend proceeding with our single sample test. Yeah.
I'm sorry, I keep asking
No,
questions for
it's
you to
good.
like create rules.
Yeah.
But what would be substantial missingness? I'm sure it depends on your sample size,
Yeah.
but like,
Just,
when are we concerned?
I don't know. I mean, if you got a handful of scores or maybe not, you said maybe note that you've got some missingness if it's a little more. Yeah, there's no dichotomy. There's no like, oh, when this is, and this is the thing, like maybe you say, boy, I'm really concerned with this sort of level of missingness, and I might write on the thing like, it's actually probably not that that bad, right? A lot of this is norms and just getting opportunities to see data and sort of work with data and then getting feedback from Matt and I. I'm not going to take points off because you identified something as terrible because it's sort of this. And I'm like, well, it's probably not too bad, right? So yeah, we'll just kind of go through and build it. It's a lot of this is just sort of thinking carefully and like, I don't know, would I be worried if it was my study and there was this number of missing values? You know, so I'm just kind of commenting on that. Yeah, Jen.
On the first page of this PDF, what do all those words mean in the
It's not the syntax.
parentheses?
Yeah, those are your syntax files and stuff like that. So we'll go through, SPSS generates those for you, so you don't have to worry about that. And we'll get into that with the next example.
Just so I'm looking at this data set
Yeah.
from the variable view, and just so I'm like understanding this correctly, your scale, so your total score, right, the thing that we did, the ascending and
Yeah.
like deleted, that's the composite variable, and
Yep.
then are those subscales above, the
Yep.
subscales within it? Okay, I just
Yep.
wanted to make sure I was
Yep.
understanding that.
Well, that's good. Yeah, and so those subscales are inconsequential to this question, but yeah, always understanding the data is sort of a helpful thing. Yeah.
Okay, and then second point.
Yeah.
The first two, participants, I guess you would call them, their, composite score and then all their subscales are 0. Is 0 a value on this
Yeah,
scale?
it's 0 to 128. So
Okay, I just want to make sure.
yeah. Now, do we think that this person has no interpersonal problems? Like, I don't know. We'll see. But like, again, that might be something, and I like getting that you're looking at that and thinking about that, because if that was sort of my thesis or like, boy, I wonder kind of what's going on. It's a real value in the scale, like people
Okay.
can score, but again, anytime we get people scoring on the extremes, kind of wonder about that a little bit, but you know, it's there for a reason. So as long as it's not too many people, we probably won't be too concerned. Other thing too is, again, what's our sample size? Big, right? So probably not too concerned that if I've got 1 or 2 people who are just flooring out that's probably not going to have too much of an impact on things. Yeah.
So going back to the previous, like,
Yeah.
from we're looking at. So when we do the problem set, do we report any, data, that is, not there, like as missingness?
Yeah, we'll go through, and so we're gonna go through a lot of these, so you kind of get a sense for kind of what this looks like. So yeah, we're gonna give you some different looks in the next example about how you might incorporate if there was. So here is, you've got 70 cases missing. So I'm not gonna ask you to go through and tell me what the case number is, the participant number is for all 70 of those cases. But if you were missing, say 3 values, yeah, I would probably want you to say like, oh, so I've got case this and this are missing their the grouping variable values for the grouping variable, and then case number 68 is missing sort of my outcome.
But
Right?
if they're big, we can just provide a percentage like they did.
Yeah,
Okay.
Yeah.
Thank you.
so, okay. All right. So gone through and cleaned this, and this is good. This is looking about as good as we can hope for, right? So what we're gonna do real quickly is we're just gonna go through and we're gonna run our test, okay? This is the thing, your screening is gonna take 3 times as long as the test, the actual running of the test is like that. It's the amount of time sort of going through and getting to know your data and figuring out what's actually going on. Here to go through, and again, if you wanna pull up your independent sample t-test handout, okay? This is just documenting this. What we're gonna do is we're gonna go to analyze, go down to compare means.
You want the independent one or the
Sample.
single sample? And this independent sample t-test or single sample?
Oh, we're gonna go single sample, so we're gonna go. Oh, yeah, sorry,
Yeah.
held up the wrong one. Your single sample. Yep, your single sample, page there. So we're gonna go to, compare means, one sample t-test. Okay, and we're gonna select that. And then we're gonna go down through and we're gonna find IIP 32, that's our test, value. So we're gonna go through and move that over. Okay. Then. What we wanna do is put in our test value, okay? What's our test value here? 25, right? Okay, 25 will keep the estimate of effect size on. If I go up to options, what we'll see here is my ability to go through, here's my confidence bound. 95 is kind of our standard here. What we could do then, we could change that to 99, 90, whatever we want. We don't need to mess around with that, so I'm gonna hit cancel here. All right. So then Jalen, this paste button right here, okay? If I hit paste,
Thanks.
what that's gonna do is it's gonna immediately take that command and drop it into my syntax file. Okay, and so what this is for my t-test that I just developed. This is just the command for running that test. Okay,
Can we, okay,
I was forgetting
can
to do that
we,
before.
do we need to do that? Can we
Yes.
take the things that you wrote and put them in there?
Yeah,
you could if you wanted to, but it's probably gonna be easier, and this is the reason we use SPSS is the pull down menu is just kind of going through and figuring it out. Is kind of a nice way to go through and make sure that you've got your options and things along these lines, okay? With state of the program that I use is let's just see an example. You don't have to worry about it. The programming language is much easier. Like it would be for me to remember, like this is all the command that I have to write out in SPSS would be a pain in the ass. So I don't worry about that. But what happens is I start to keep doing, and you probably will, just because different screenings will be very similar for different problems. And probably what I would encourage you to have is probably just like a screening, sort of like a demo file that you can go through. And once you start to become familiar with how this looks, then you can just start sort of copying and pasting from your own stuff and swapping out variable names and stuff like that, and just go through and do it that way. But for applied analysis, the nice thing about having this is you can go through in this file and start making comments. So anything you start with an asterisk is going to be read as a comment. So it's not going to go through and run that as a command. And so I can go sort of do that and say, running single sample test. Okay. And what you can start doing is you're making a record of the analyses that you've gone through and done, what different commands are doing, why you're doing it. This is going to be incredibly valuable as you're going through and actually sort of running your own data so that you remember what you did, what you were thinking, and why, and things along those lines. Yeah.
So my, when I did that, my output popped up, not the, how do I open the syntax?
So we should be, when we're doing this on our own, we should be going to the paste and pulling this,
Yep, and just
and then you can press.
and pasting it in. And then what we can do here, so what I can do is I can just highlight this
Okay.
and just hit run. And there's my output.
And another thing you can do is like, if you click on this button, like it'll show the last test you ran, you can go back to it and just hit okay, and it'll also run it.
Yeah.
Oh.
So like
Alright.
click this button,
So,
shows like the last test you ran. Oh, great.
all right, So a lot of this is just gonna be going down through and just becoming from a show of hands, who's used SPSS like syntax files before?
Years ago.
Okay.
I use it to recode variables all the time.
Okay.
And then I have to redo everything all
Yeah,
the time.
no, and this is the thing that is, as you start to get to graduate level work, having this as a record of what I did, how I arrived at things, and even SPSS is still not managing data within SPSS is still kind of a pain. Programs like Stata and R, where it's more command prompt types of stuff. What I can do there is just I have like my raw archival data, and then I've just got a string of command that says drop anything with values greater than this, drop this, recode this. And then what I can do is I can just run the whole thing on the original data set and come up with the same thing every single time. That's a nice way to go. SPSS is nice because you're kind of mucking around doing things by hand. But then what you do is you create data sets that you forgot how you got there and then have to go through and try and backtrack, trying to remember what did I delete? Why did I delete? Did I change anything, any scores and things along those lines? So just in general, keeping good documentation of what you're changing in your sets and in your analyses is always going to be important. It's going to save you a tremendous amount of time, as opposed to having to go back and trying to remember what Allison from 3.5 months ago was thinking when she was running whatever it was you're running. Okay, so I spend a lot of time trying to figure out what the hell Past Josh was doing at the same time. I rarely trust Past Josh. Past Josh is generally right, but I still have a healthy skepticism of him and what he's up to. So if we go through and take a look, now this is probably hard to see here, but okay. So, all right. So here's our output. Pretty straightforward. If we look at so again, yeah, Jim, this is that top piece is just walking through like what pull down menus you find. This is just your actual syntax statement here. And so if we go through and we take a look, this is just our descriptives. Okay. We're just wanting to make sure that sort of these descriptives make sense with what we know. Yeah, our sample size is right. So that our mean value is right. Okay, this is all looking good. Dropping down, if we take a look at our one sample test, our test value under the null is 25. Here's our t statistic. Here's our degree of freedom. Here's our two-sided p-value. The mean difference between my sample and the sample under the mean, or sort of, excuse me, my sample or my test value, and then my upper and lower values for my confidence bound. Okay. Looking at this, Allison, give me an interpretation of that confidence bound.
Lower bound is 37.69 and the upper bound is 42.01, so, or sorry, I'm looking at the wrong thing. 12.69 is the lower bound
The
and
lower bound of what?
of the, like, compatible value, like, estimated values
Estimated value of what?
of the sample, or the, I don't know.
Okay, this is because this is tricky, right? Because we've got a 95% confidence interval, but a 95% confidence interval around what?
Difference.
The difference. Okay, so if we go through and take a look, we could, and in the library example, what we did is we created a 95% confidence interval around our point estimate of the mean, right? But if I'm looking at this is my point estimate of the mean. Why do I know that it's not a confidence interval around the point estimate of the mean? Means way the hell outside of it, right? So wanting to go through and make sure that we understand what's happening. What SPSS is doing is it's taking the difference between your observed value and your test value, and it's creating a difference there, which is giving us my mean difference of 14.9 to about 15 points. Okay, and so what my confidence bound as SPSS is going through and calculating it is giving me the lower bound of the difference from my reference value and the data supported, upper bound of my data supported difference there.
So, I guess so this is telling us that, well, our population mean is 25, right?
Yep.
Okay. And didn't we talk about how we know if like our confidence intervals are like reasonable as if it's between, if like our population mean falls in between them?
Okay, is this a confidence interval around a population mean? No. Do I need a confidence interval around my population mean? No, because my population mean is the population mean. So here, remember with a one sample test, we're assuming that we have some population mean or a reference value to test against. So that 25 just is what it is, right?
Okay.
What we have uncertainty around is for, so this is a good question. Who's my reference population? What reference population am I interested in here? Really?
Like what's,
Who did I sample from? Who did my sample represent?
oh, I'm trying to find where that. I can't remember what you said. I know it's like the people that.
College kids who have trauma, right?
Okay.
So what I've got is I've got a population value. I've got a population value and an estimate for IEP for this universe of adults, and we'll call that 25. Okay. But this isn't who I sampled from. I have a sample of undergraduates who experience significant trauma, right? And so my hypothesis, my alternate hypothesis is that this is a different population with a different characteristics than the general population. And so what I'm saying is I think that this is maybe the distribution of IEP scores for college students with trauma, right? And I think that this population has different characteristics than show my reference population, but I don't know. I have to run my test to see that, right? And so what I've done is I've got a large sample, 334 trauma exposed undergraduates, and then I gave them this measure. And when I do that, I find that they have, what's my best guess for the population mean of trauma exposed undergraduates? Yeah, it's right there, 39.85 for about 40 points, right? Now, I know that estimate is going to come with there. Do I think that's actually the population value of all college students who have experienced trauma? No, it's my best guess. But what would be, based on the data that I've collected, what would be reasonable upper and lower bounds for that? Now, SPSS doesn't give those to me. What SPSS gives me is a difference between those two, and then the upper and lower bound for the difference, right? So this is telling me that based on my data would support anything from about a 12.7 to a 17-point increase in IEP scores relative to the normal population, right? Yeah.
Okay. Confidence intervals always mess me up. I'm very confused with what they're telling me in comparison to the number we have. Do we reject the null? Do we want our mean difference to be in between the lower and upper?
Okay. Because this is what I've calculated, my difference has to be between the
So
lower
it
and
has,
upper. Yeah.
what if it's not?
It's impossible.
Okay,
It's defined wrong. Okay, so what value would I expect to see in this confidence bound if I were to fail to reject?
The population or
Like 18 or.
Yeah,
Wow.
there you go. Why?
then there wouldn't be a difference.
There wouldn't be a difference, right? And so this is why, yeah, no. So this is why, so wanting to go through it, it's so critical to go through and not just look at these as numbers, right? And just say like, oh, this gave me some numbers and this is an upper and lower bound, like, well, yeah, technically, but like unless you sort of understand what it's a upper and lower bound of, it's hard to try and tie it together, right? And so this is always, anytime you get an output from SPSS, you should be able to walk through and sort of tell yourself what every single thing in there represents, okay? Now, what we had done in the library example is we had gone through and calculated, say, old librarian says the age of books is 20 and we find it to be 25, and then we calculated confidence interval around sort of the point estimate of what we've got. What SPSS is doing is instead of that, it's going to go through and do something a little bit different. It's going to give you the mean difference between sort of these, because again, remember, our t-test here is going to be my mean minus the expected value under the null over my standard error. This is just giving you that that numerator on that, right? And because it's giving you the numerator on that, then it's going to go through and it's going to calculate a confidence bound, not around this, but around that difference. Okay. Now, if I were to calculate the margin of error for that difference, and we'll just tack that onto that, it's going to give me the same thing, right? It's going to give me the plus or minus. Like I can go through and easily with this. I mean, if I go through and take my, does it give you standard? Yeah, it does. Standard error of the mean, right? So if I were to go through and take 39.85 plus or minus 1.099 times N of Z. My critical T for T with 330 degrees of freedom is going to be functionally 1.96. I mean, at that point, we're basically at a Z table here, right? If I were to go through and do this, this would give me the confidence bound around that. But my margin of error, this is going to be the same margin of error that's gone through and being calculated for that difference, right? So it's just making sure that you understand, looking at that and using what you know about interval estimation and what's going on to make sure that you understand what these different values mean. And then you can start assigning sort of meaning and value and interpretation to this. Okay.
Sorry. How do we say that?
Okay, I'm gonna give you an example of interpretation, so we're gonna get there. Yeah.
If our sample mean were like 20, or lower, would our is our mean difference an absolute value, or would we get a negative?
You get a negative on that, right?
Okay,
And that would
gives
just,
us some direction.
yeah, that would just give you a little bit of directionality, but always make sure that you're sort of thinking about that, because sometimes if I go through and swap that around
Right.
on accident, it's not gonna change anything, but it's gonna make things look like they're going in the opposite direction. But it doesn't matter so long as you understand that, right? Yeah.
So, but you said that we typically don't know the mean for the population.
Yeah.
So if that's the case, so like right here, you gave us 25 as the population mean. Is this just like to learn for
Yeah.
fun, but realistically, this is
Mostly
like.
for fun, a little bit to learn, but.
Yeah, I just want to make sure that I'm like, okay, realistic.
No, you're exactly right, because this is the thing, like, we don't run into a lot of single sample teams.
Okay,
Just because it's rare that we're going through and testing something against a point estimate or a reference value. We should probably do it more often, right? This is getting to some of the stuff that Neil is talking about, like, does zero have to be our, like, so that the point of value is exactly zero? Does that always need to be the case? Probably not, but in real life, it's rare to see some of these. But this is essentially what we're doing with the single sample T is basically just an extension of your single sample Z test. It's just, we don't know the population standard deviation, but we're assuming that we know or have a guess for the population value or some reference value. Okay, and that starts to become important when you're thinking about approaching this next problem set, recognizing that, like, I have a sample with some unknown characteristics. I want to test against some a priori value. How do I go through and do that? This is your option. All right. Other thing too that we're getting down here. So I guess, yes, very clear evidence, right? Strong evidence. That's a massive T statistic. Very, very small p-value here in terms of what I'm doing. Here we have my effect size here. Here's my standardizer. Here's my point estimate. Here's a confidence bound around this. Okay. Remember, for single sample T, this starts to become easy. My D is just gonna be the difference between my mean and my expected value under the null divided by my standard deviation, right? So someone take for me 14.85. Abby? Okay, 14.85 and divided by my standard deviation, 20.092. 739, okay. No magic in terms of where that's coming from. It's just going through and putting things together. Then I have an upper lower bound and my confidence bound. This is tricky, and something new that SPSS is included in, which is good. But this is just saying that estimates of the population effect based on these data ranging somewhere from a potency of 0.62 to 0.86, right? And so what I would say is very literally, this is telling me that interpersonal difficulties in, based on the data that I've collected, interpersonal difficulties in university students who have experienced trauma appear to be close to 3/4 of the standard deviation above what we would expect in the normal population. Which technically doesn't hit that large effect size, but that's still pretty substantial, right? Other thing that we would do is here it's a little bit tricky because we've got a very small p-value. If I wanted to go through and calculate S value and a base factor bound for this, I can't just drop 0.001 in there, right? But if I go to my output here and double and click on this, it's going to give me 1.8668 times 10 to the negative 33. That's an extremely small p-value, but what we're going to do is if I want to go through and calculate no, I don't want to do any of that stuff.
Yeah.
That's okay, Josh. I'm too excited to do this. I just keep.
Right now, there you go.
Okay, so if I go. Yeah, so if I go here. You don't, you haven't created it yet, but you will.
Cool.
I was gonna ask you how we could find the exact p values, so I'm glad you told
Yep.
us.
So we go down here, and so what I'm gonna do is I'm just gonna take that p value. Come on. It's gonna make me sign in to go through and do this, but if I go through and drop this in here, it's gonna give me my S values here. Now, if I've got an S or a p value that's 0.046 or p value that's 0.008, I can go through and calculate that by hand, right? And I'm gonna ask you to do that just so I know that you know how to go through and do this, but setting up a sheet like this is gonna be easier and more efficient way to go through and calculate this stuff, okay? So, let's do this. Let's go through and take a break. Let's come back at, so just let's get back at 4 and then we'll get to be back here at 4 ready to go and we'll jump in the rest of the stuff.
Do you think any more just slides today or is the rest of it demo?
No, we'll go through and
Just slide, okay.
I'll email you, but I'm gonna be gone.
I don't know. I know, I just. It's like very in the world. But then I'm gonna. Yeah.
All right, folks. I'm gonna jump into your break a little bit quickly, just so we can go through and get started with stuff. I guess questions about, and we're gonna go through slides here that just kind of tie all this together in terms of how do we take the information that we've got and sort of pull it together into a consistent interpretation. But any questions about where we're at this point?
What?
Questions? Hang tight. Hang tight with it, okay. All right, so in these slides, here we're just talking about our single sample t-test, right? And so this is just kind of showing you how to go through, grab it, in your pull down menu, what this looks like in your syntax and stuff like that. Putting together, like actually writing out the syntax is not an efficient way to run through and do things in SPSS. Just becoming familiar with the pull down menu, but once you've done these, and if you just have like demo or stock syntax files and are comfortable swapping out things that you become comfortable with, you can go through and do that, and that'll save you some time, okay? Here's our output. Again, here's our descriptors. Always want to check that to make sure that those are consistent with what you think should be going on in the data. Here's our one sample test, right? Massive p-value, very large sample, very small p. Here's our mean difference, and then the confidence bound around that difference, which in this case is actually pretty useful because it's literally telling us data supported estimates for how much higher we're expecting undergraduates exposed to trauma to report in terms of interpersonal difficulties on this measure that we've given them, right? Now, what does a score of 75 on the IAP 32 mean? I don't know. No one does probably, right? So what we've got down here is a way to go through and standardize the magnitude of that effect in terms of calculating Cohen's D. This hedges correction, that's something a little bit different. You don't need to worry about that too much. This is just a correction for your effect size to account for small samples. We'll talk about that in a moment. But with 334 people, you go through and just look at this. And if you look at those two, those are functionally identical numbers anyway. So you can start to see at that sample, that correction sort of starts to become negligible. And then confidence bounds around your effect size. We'll get more into confidence bounds around effect size, why these are kind of complicated to calculate. But these confidence bounds are going to be interpreted the same way as any confidence bound are interpreted. Here's my point estimate of my effect. And based on the data I've got, my data supported values for the population effect load range is supporting anything from an effect size of 0.62 to 0.86.
Sorry for this super annoying question. So what number would we need to get to reject the null hypothesis?
On what?
Like, in terms of like the confidence?
Confidence bounds for what? We got confidence bounds here, we got confidence bounds here.
On the one sample test.
On the one sample test, okay. What is this, Mandy? What is this a confidence bound around?
Upper bound, that means like where, based on like, if our value falls within or.
Sure. Well, what is this a confidence interval around? What's the point estimate that this is referring to?
Point estimate this, like both of them are referring to?
Yeah,
The lower bound,
what's fine. So here we've got a mean difference.
that is like within the confidence.
Yeah, right. So if this is the mean difference between the sample that I've drawn from my population of university undergraduates who've been exposed to trauma relative to the general population of people, adults, right? What value would need to be contained in that interval in order for us to say that we would probably fail to reject the null?
I'm thinking like anything outside of like below 12 versus outside of.
Well, I mean, so those are just data supported values for the point estimate of the difference of about 15 points. What difference value would suggest that there is no difference between trauma exposed undergraduates and the general population?
Would it be the same thing? That would make it 0 or something?
Yeah.
And so if 0 was in there, we would say, well, it looks like I thought maybe just based on what I know about trauma that maybe university undergraduates who've been exposed to trauma might report on average higher levels of interpersonal difficulties than just people at large, but I guess they don't, right? Maybe this difference, maybe the actual mean that we get is 26, right? We've got a difference of 1, right? And we've got a lower bound of -3 to 8 above, right? That would suggest that 0, no difference, would be a reasonable guess. And so then you would be able to reject it, okay? So this is just like making sure that you're going through and understanding what these numbers correspond to, always know, so what's my point estimate? What's my interval estimate around that? And then making sure that sort of everything's matching up. So in Stata, same thing, Johnny. This is just, I mean, versus all of that, right? With this language, it's just t-test, IEP total equals 25. And then that gives you sort of all the same stuff that will correspond directly with that. So just a little bit language, a little bit different language here, but it'll give you the exact same results. Okay, so if we're gonna go through and pull this all together and write this up, our sort of first is tell me the null hypotheses in actual sort of words, language. We're saying the mean score for IEP 32 interpersonal difficulties in the larger population of undergraduate survivors is mean equal 25. Okay, what I'm wanting you to do here is be very explicit, like tell me that you understand what population that you're pulling from, right? And here we're saying that we're pulling from IEP difficulties from university undergraduates who've been exposed to trauma, and under the null hypotheses, we say that their mean value should be identical to what we see in the normal population. Okay, we're to write that in statistical notation, pretty easy, right? Mean value for population value for IEP is 25. Alternative, it's not 25. Okay, these are two-tailed tests. Our confidence bound around the difference or the discrepancy that we're seeing in our sample mean versus the expected value or the reference value ranging from 12.7 to about 17, right? T-test, our p-value here in scientific notation, okay? Wanting you to start feeling comfortable reporting these in SPSS, you just double click on that and it'll pop up the actual value. Please don't cut and paste that in because it'll be an obnoxious number. Just go through in a few decimals and notation there. Johnny, you won't be able to do that in Stata, but you do set up an Excel file to just drop that t-value in degrees of freedom and it'll give you the p-value for that too. So this is my effect size, 0.74. If I go through and if the computer was cooperating, I could drop that very, very small p-value into my S value and base factor bound calculator, I would get an S value of 109. Okay, so thinking about this, we'd say for these data, evidence against the null hypothesis of a population mean of 25 on the IEP 32 and undergrad trauma survivors be similar to that of observing 109 consecutive heads on tosses of a hypothesized fair coin. It's functionally, it can't happen. Like assuming that I've collected my data well, this is functionally impossible to get a sample of 335 individuals and get that. You know, we're essentially saying that if the population value of IP for university undergraduates is actually 25, right? The probability of me collecting a sample of this size and getting a score that I got is something way out there. Like it functionally can't happen. These data are completely incompatible with the idea that the average IEP scoring university students exposed to trauma is equal to 25. It's orthogonal with that, right? And we could say, well, yeah, we knew that P less than 0.05, for sure it's a different effect, but this is really kind of looking at like how incompatible these data are with that null hypothesis. Same thing if we go down through calculate our base factor, 2.67 times 10 to the 30th. That's a massive number, right? So we'd say database odds for alternative hypotheses of population mean other than 25 and for a two-tailed test are at most 2.67 times 10 to the 30th times that of equal scores across undergraduate trauma survivors and members of the general public. So we're just trying to sort of incorporate this in. This is an exercise for you to sort of demonstrate that you understand kind of what these mean, but then also sort of clarifying what our populations are, who we're comparing, who we're thinking about with this problem. Okay. All right, and then the write-up. Okay, this. So we say so. This is just an example, right? So this first bullet is just sort of making sure that we're sort of understanding exactly what's being compared and things, right? So we say single sample test used comparing interpersonal difficulties reported trauma exposed undergraduates relative to normative scores from the adult population. Null hypothesis posits no difference in interpersonal difficulties in undergraduate survivors relative to general population. Okay. You don't need to do this, but it's a nice way to just kind of orient yourself to and organize yourself. Like, what are we actually asking in this test? Like, what are we doing this for? What's the question? Okay. So again, not something that I necessarily am going to sort of say that I'm going to take points off if you don't have it. But again, have been doing this long enough, and I think the struggle will happen is people try and just jump in and start like saying stuff without getting organized around stuff. And it can be helped to just kind of ground yourself and sort of just remind myself, okay, what populations am I comparing and what's going on here? This, you don't need to worry about this, just kind of and don't do this, because if you put it in, then I'll have to read it. And if you get it wrong, you'll have to take off ones. You're gonna have a data screening summary like we already sort of went through and looked at. So you don't need to worry about this. Don't sort of put that in there, okay? Here's where we start getting into sort of actually what's going on, right? So we've got trauma exposed students in the current study evidence of mean IEP of 39.9 standard deviation, which is consistent with the 3/4 standard deviation increase in interpersonal difficulties relative to the root score reported in the general population, right? And there's my D, that's that 3/4 of a standard deviation increase. Population differences across trauma exposed students and normative adults ranging from 12.7 to 17 found compatible with responses in this study, right? Just kind of going through, giving an interpretation, a meaningful interpretation of that confidence bound. A single sample t-test identified the data as highly incompatible with a null hypothesis or with a null model specifying a population average of 25 in trauma exposed undergraduates. And then we just got all our test statistics there, right? So just going through and trying to take what we've got and integrate it in a way that communicates to somebody, this is what we found, this is strength of evidence for stuff, pulling it all together, okay? So this is all the technical things. Then we get down, and this is arguably the most important piece here, saying results of these analyses offer support for moderate to large elevations in interpersonal difficulties among trauma exposed undergraduates with some level of event-related distress, okay? Where did I get moderate to large elevations in interpersonal difficulties? Yeah.
The effect size.
Yeah, the effect size, right? My effect size is sort of right there around that large-ish, but if we look at the upper bound on that, it was sort of clear. So we got some reasonably large things going on here. You say, why compelling? Missing this in the larger data set introduces the possibility of response bias, which could in turn influence estimates of interpersonal dysfunction, right? So we, again, going back, remember we 70 scores that we went through and nuked off of there. Now, I know why those scores are gone is because we early on didn't have those scores in there. So it's just people didn't have the opportunity to respond. So this technically isn't a problem because that missingness was by definition sort of functionally at random. But I don't know that. All I know is you had 7 missing scores. I have about 20% of your data. So want to go through and talk about that. I would say it's also important to note that participants in the study were substantially younger, more predominantly female, and more highly educated than respondents in the normative community sample. As such, we're unable to determine from the study whether elevations on IEP total scores are associated with trauma exposure or attributable to some other factor, right? I've got a completely different population. There's lots of other stuff going on, right? So based on what I know about trauma, I would say probably has something to do with it, probably contributes, but there are some other things that we would want to go through and think about in terms of our interpretation, okay? And so this is just kind of pulling everything together and trying to say something substantial and meaningful about the question at hand, okay? Now, this is like an idealized example. Please don't try and like sound like me necessarily, because I want you to use words that make sense to you and to Matt and I, and sort of just trying to plug and play my stuff won't, but sort of just trying to give you an idea of how you might go about trying to synthesize some of this information in something that communicates stuff, okay? Obviously, if you're writing for like a publication, like you can't spend that much time talking about an independent sample t-test. This isn't a publication you're writing for me, so that I understand that you understand what's going on. Something that might be more streamlined, right? Just a quick statement on screening, maybe just a quick sort of consolidation here. But notice that we did this, like who's confused about what this means or what it implies, right? we did all of this without mentioning significant effects or sort of making dichotomous decisions on anything, right? We're just saying like, this is what the evidence says, this is kind of where work bounds are. And so breaking away from just saying like, oh, there's a significant effect, which doesn't tell me much of anything. There's just so much more. Here we can actually talk about this, start to create meaning, and thinking about the possible impacts of trauma on the interpersonal functioning of young people who have sort of trying to navigate some of this stuff, right? So incorporating things in a more meaningful way than just making yes, no decision about sort of an effect or not effect. Okay. All right. Does this help kind of seeing how we might kind of start to pull this stuff together and incorporate information? Yes, yeah.
I do have a question, but if this would be a better question for office hours, that would be
Yeah.
fine too. But I am like still slightly confused about like the like S value and like the BFB. And
Yeah.
like, I was wondering if you could maybe try to explain like what it means in this context.
Yeah. This is just massive. I mean, it's just really, really big. If we're thinking about our tests as assuming that the null hypothesis is true, what are the likelihood of these data? Well, assuming that undergraduate trauma survivors have a population mean value on the IEP of 25, these data functionally can't exist. You know, and this is just different ways. I mean, if you look at that p-value, that's very obvious.
Sure.
So that S value, like, so we would say that evidence against the null hypothesis provided by these data would be similar to evidence of 109 consecutive heads on a hypothesized fair coin.
Okay.
You know, here we would say that the likelihood of the alternative hypotheses that the mean value of IEP scores in the population of college students experiencing trauma, right, is different than 25, is about 2.67 times 10 to the 30th times more likely than the null hypothesis that it's equal to 25.
Okay.
I mean, just substantially. This is now we can criticize maybe the way we went around and collected these data, right? And so do these actually represent all university students exposed to trauma? Sure, but absent that, like these are very, very clear and unambiguous data. I would have no concern about these sort of replicating. These are pretty convincing stuff. Okay, but we'll get into things where we would normally say reject the null hypothesis, where things start to become a lot more ambiguous. Questions on this? All right, cool. Okay, so just another sort of so Mr. T. So, I mean, that's you know the thing where you can get celebrities to leave you voicemails.
Yeah.
I mean, so maybe I'll see if Mr. T's on there and see if he can give.
I'm gonna read this book, it's a quote right here.
Yeah, that'd be awesome. All right, cool. All right, so all this is good. Having a good time with this. So we use Z's and T's to compare a sample mean to a known population, but these single samples D tests and T tests generally have more information than sort of what we would typically want and apply stuff. More commonly, what we're wanting to do is we're wanting to look at comparing means from samples pulled from a couple of different populations with unknown means and standard deviations, right? And so this is where we get into our independent sample T test, okay? Independent sample T, what we're doing here is we're looking at differences between two populations in theory, right? What we've got is we've got two populations that we would like to compare on some outcome, but we don't know what the parameters of those populations, what those two populations are, okay? This is one of our most basic fundamental experimental designs. This independent sample T test is a foundation for everything else we're going to do for the rest of this semester. So we really want you to be comfortable, sort of at a conceptual level, understand what's going on with these comparisons, okay? So again, I want to know if I see differences in learning outcomes in population A taught by method A, population B taught by method B, right? I don't know what those population values are. In theory, if everybody, all students got population or method A, what would the scores be? If in theory, all people got population or method B, what would the values be? How do I go through and compare those? I can't sort of compare those directly. What I can do is I can start drawing samples from those and look at those samples to try and make an inference about likely difference in those two populations, okay? So for my independent sample t-test, my null hypothesis is that population mean of 1 minus population mean of 2 is equal to 0. Okay, you could write this as population 1 is equal to population 0, but that's not actually what's being tested mathematically. It's mathematically testing whether or not the difference score between these two things are equal to 0. So this is going to be the more appropriate way to go through and write that in statistical notation. We're saying the difference between population means is 0, and by extension, scores were likely drawn from populations having equal means. Okay, that's our null hypothesis. For alternate hypotheses, again, 1 minus 2 is not equal to 0. Difference in population means some non-zero value, right? Again, this is how we always run things, but again, getting back into some of that meal stuff, like Neil saying like, well, just because something's not 0 doesn't mean it's interesting, or sort of if this is never the case, right? We're gonna fall sort of anything, even if it was, we're gonna fall on sometimes on one side, sometimes on the other, right? But this is how we set up our tests. Our observed scores are unlikely to have occurred if the means from the respective populations were equal, right? Essentially what we're doing is we're gonna say, we're gonna draw from population A, we're gonna draw from population B. We're gonna see what type of discrepancy we get in those means and try and determine using our statistical methods whether or not we have enough evidence in that to say, yeah, assuming that these populations have equal means, the differences that we're seeing in the samples of the size that we've drawn is very unlikely, right? Which is a different thing than given the data, what's the likelihood of the null hypothesis, but we've already talked about that. We can't do anything. We can only work in the system that we have available to us. Right? So again, the main question that we're trying to do is see if the different scores between the two samples are sufficiently large to determine they were drawn from populations with different mean values. Okay, this is super important. People understand kind of what we're really trying to ask or get at with our independent sample t-test. All right, assumptions of my independent sample t. I'm assuming again, I have my outcome variable is continuous or something that I can at least treat as continuous. The observations in each sample are independent. We talked about that. Distribution of sample means for each population is normal, right? Again, I don't have a specific assumption about the data I'm looking at. My assumption of normality involves the distribution of sample means, okay? And again, Danielle, when do I know when the distribution of sample means starts to become normal? What are my two conditions?
If you have a large sample
Got large
size
samples.
and if what you're looking at is already normal.
If it's already normal, both of those things, distribution of sample means is going to start to become normal very quickly. The thing we're adding in with the independent sample t is a homogeneity of variance assumption. Okay, what we're doing is technically within the context of our independent sample t-test, we're assuming that the variance of both of those populations I'm sampling from is equal. Okay, so whatever I'm measuring in people taught with method A and people taught with method B, whatever that learning outcome is, I'm assuming that the variability in both or the variance in both of those populations is equal. Okay, and if there's not, then it starts to sort of impact the strength of some of the inferences that we can draw. Okay, informal assumptions, data not collect that contain outliers. We talked about that, and also with our independent sample t-test, there's just an implied assumption that these samples are relatively equal across groups. And this is a remnant of, not a remnant, but just a function of these means-based tests and these methods were all developed within the context of experimental research, right? And if I've got an experimental study, right, Gabe, you've got people coming in for your thesis, are you going to randomize 90% of people to one sample or one condition and 10% to the other? No, it doesn't make it. You're in charge of who gets what condition. And so in general, like the assumption is like, yeah, things are pretty even, right? Now, when we actually go through and do this into actual stuff, if we're looking at existing characteristics, measured stuff, oftentimes we won't have equal samples because not, particularly if you're doing clinical stuff, not everybody is going to come in with PTSD or eating pathology or substance use issues or any other such type of thing, right? So we violate this all the time, so we've got to keep an eye on it and the potential impacts with things. But in general, we're assuming relatively equal representation across groups.
Oh, I have a question. So I'm trying to think related to like the things I'm interested in.
Mhm.
So if I were to collect data from UW and another university, I would hope that the variance in both population is equal, and so I would use a t-test.
Yeah. But we're gonna go through and test whether or not we have evidence for that assumption or not. So we'll go through and take a look at it. Yeah. Okay. All right. And then once again, all of our auxiliary hypotheses, these are always going on in the background, right? These are the situations under which our tests were developed, right? And when these things all meet, then we have very strong confidence in our interpretations. As these start to go away, we have to start carefully and thinking about like what are the potential impacts, right? So this is something that we all just hide away and repress deep down into our subconscious, but they're there. It makes them no less real. Me not wanting to think about that doesn't mean they go away. I can probably get away with it a lot of times, but if I'm thinking about advancing science and sort of thinking about sort of the precision of my effects, these are all things I need to be thinking about. Okay. So formula for independent sample t-test, pretty straightforward. What we've got is in this numerator, we've got the mean of sample 1 minus the mean of sample 2 minus the difference between expected difference between population 1 and population 2 over the standard error of the difference in means. Okay. Now, in actual fact, that just kind of cancels out. That goes away. Why?
Because we assume it's 0.
Yeah, we assume it's 0. We assume the population mean of 1, population mean of 2 is 0. Does it have to be 0? Nope. We can go through and test against whatever. I could, and again, getting back to that meal paper, I can very specifically test if I wanted to say, I think that population A and population B are gonna have a difference of 10 points on this outcome. I can go through and test my value under the null doesn't have to be 0. I can just set that up very easy for the value under the null to be 10, right? And everything works exactly. That's not how we do things. We should probably think about doing things, right? The problem is just with the level of precision of our measurements and things along those lines, we rarely have enough information to make that point estimate or to sort of make a decision on that. But again, that sort of gets back to thinking about like our science, how we do things and how we might improve if we want to start getting fancy with stuff. Okay. So in the denominator here, we have the standard error and the difference in sample means. Okay. Here, standard error of difference in sample means is the expected difference in means across samples, assuming that the null hypothesis is true. Okay, before with our single sample tests, we're looking at the standard error of the mean, same concept. Now we just have the standard error of the difference in means. Okay, so basically what we're doing, we're still talking about this as a standard deviation of the standard error is a standard deviation of distribution of sample means, except now it's just the standard deviation of the distribution of difference in sample means. Okay, so if I were to take all possible samples of sample size X from population 1 and all possible samples of sample size X from sample 2 and subtract those two differences, what would I get in terms of the different distribution of these different scores? So now with our independent sample test, our distribution of sample means isn't mean estimates, it's differences in means. Okay. Now the problem is when I'm sampling from 2 independent populations, I've now got 2 sources of error, right? So I'm going to go through Haley, and I'm going to pull my sample from population A, and I get a mean samples. My sample value is 46.
Like your mean?
Is my mean.
Oh, okay.
How confident am I that that perfectly represents the mean of the population? I'm not, right? There's going to be some stuff there. And Jalen, you go through and you collect a sample from population B, and you find a mean value of that sample for 56. How much do you expect that, or how confident are you that that value is exactly the population value from that group? Right. So what we've got now, instead of just having variability and error in one sample, now we've got 2 samples to account for error, right? right? And so what ends up happening is we need to go through and account for this. And so as a consequence, the estimate of our standard error for my independent sample T has to take into account both sources of error. Okay. So what we do for the calculation of our standard error for the difference in sample means we've got the square root of the variance of sample 1 divided by the sample size plus the variance of sample 2 divided by the sample size. Take the square root of that. Okay. Before our standard error, remember it was just right? Just 1. We've essentially doubled this. Okay. But if we double our standard error, what happens to our test statistic? Yeah, what is it? It goes down. Our test statistic goes down, right? Just reading all your nonverbals here, right? So they're reading this, like, you're right all the time, so it's working out for you.
But when you call me, I'm not right,
Right.
so we should keep up.
So what we're essentially doing is this sort of where I'm running my independent sample test, where I'm essentially doubling my standard error because I've got 2 sources of error where things can be coming from here. Okay. So if we start thinking about what this means from a conceptual level, okay. I've got 2 randomly, I've got 2 populations, right? And I'm thinking about the range of possible range of any 2 randomly selected samples from population 1 and population 2. This is what I'm doing with my t-test, right? I'm taking a random sample from population 1, random sample from population 2. If I go through and I take a random look at the range of population 1, samples that could be collected of whatever size I'm getting range anywhere from 25 to 95 with the actual population mean of 70. Population 2, I can go anywhere from 15 to 65 with a population of 50, right? So if I look at these 2, I see that these 2 populations do have different mean values. One's lower, one's higher, right? But the variability looks like a little bit different, okay? So if I am trying to think about what's the possible range of any 2 randomly selected scores from these 2 populations, on one extreme, I could get the highest score on population 1 and the lowest score on population 2 gives me a difference of 80 in terms of these samples, right? But on the other extreme, I could pull the lowest score from population 1 and the highest score from population 2 and get a difference of negative 40. So on one extreme, I've got an advantage of population 1 by 80 points. In the other, I have a disadvantage of population 1 of 40 points. And if I go through and I plot this out, I have a possible range of about 120 points that could be drawn from any 2 randomly selected samples from these populations. That's a lot, right? And so what I need to do is not only do I have variability in this, I also have variability in this. With the single sample test, do I have variability in my reference value? No, it just is what it is. Like that's, so I don't have to worry about sampling here and there. But if I'm pulling from 2 unknown populations, I could get anywhere from way at the high end or way at the low end, way at the high and low end. And what happens is that, so mathematically, that could be any difference from a negative 40 one way to 80 positive the other way. That's a lot. That's a big range, right? So this is how we do it on a number line, but really if I just go through and add those ranges up, I still get the same amount, right? So just all of this to say is that when we're going through and we're calculating the standard error of our difference between 2 means, it's an additive function of the variability within each sample, okay? And so we need to take into account 2 sources of error with this, which increases the uncertainty of our test statistic, just because there's a lot of variability, a lot of different outcomes that could happen. Now, in general, we're hoping that when we pull from population 1, we get something around here. When we pull from population 2, we get something around here. But at our most extreme, we can go through and have sort of these things going in way opposite directions. Okay. So people understand sort of what starts to compound our standard error. And so if we looked at the standard or the distribution of sample differences, that starts to become much wider than it has been before. Okay.
Hey Josh.
Yeah.
Can you say where we got the ranges from again? Like the 95 is from?
95. So if I go through Mandy and I said I happen to get as high as the biggest sample I can pull from population 1.
Yeah. And the
and compare
lowest
that
from-
for the lowest for population 2, that gives me a 70-point advantage for one.
And then what's the second one?
Well, if I were to flip this on its head and I were to get the lowest score that I could get from population 1, compare that
Nice.
against the highest of population 2,
Okay,
I get a 40-point advantage for population 2.
okay.
Now, is
Because I
population 2
thought-
bigger than population 1?
No.
No, it's not, but that test statistic suggests it's 40 points bigger, right? So it's just looking at the possible extremes of this. All right. So if we go through and take a look here, this big N is just the sample population or my cell size. Well, we get into an issue. What happens if my cell sizes are different, right? What if I have one sample with 10 people in it and another sample with 30 people in it? Okay. What we know about samples is that large samples provide a better estimate of our population parameters than our smaller samples. Okay. So Johnny, in this situation, which of these samples is giving me a better guess on the which of these samples is giving me better precision? Sample 2, right? It's still small, it's not great, but it's better than 10, right? Should I weigh those two samples equally in terms of trying to calculate a standard error? No, because one of them is going to be a more precise estimate than the other. And so what we need to do, and this often happens, is we start to go through and we get different samples. How do we go through and address? How do we go through and address that? Okay. This is where our homogeneity of variance assumption comes into play. Okay. But we assume with our homogeneity of variance, with the independent sample t-test, we assume that the variances are equal across both populations, right? But when we go through and pull our sample, the variances of our samples are never going to be 100% identical. Right? So we got to handle this some way, okay? And if we then go through and throw unequal sample sizes in, smaller sample is going to have an undue influence on my estimate of my population parameter if I'm just sort of going even Steven, right? If I just say, oh, I'm going to take the average of the two variances, the sample that has less people is going to have undue influence on sort of the estimate of my standard error when it shouldn't. This should be kind of weighted out, right? So what we do is we go through and we create a pooled variance, okay? So my pooled variance is going to give a weighted average of my two sample variances. And the way we go through and we do that is we just take degrees of freedom. We take n-1 of sample 1 and multiply that by the variance plus n+1 or n-1 times my second variance. And I take all of that with n1 plus n2 minus 2, which is my degrees of freedom for the overall test there. Okay. And what this does then, Mesa, here in with this formula, I've got a sample size of 50 and a sample size of 100. Which one of those is going to contribute more to my final estimate of my pooled variance? The 100, right? Because it's going to be 99 times whatever that variance of that sample is multiplied by 49, whatever the second one is. The assumption of my independent sample t-test is that these variances in the population are equal. So I'm not worried about which one is better or whatever. But what I'm going to say is I'm just going to give more weight to the sample that's going to be more, that I'm expecting to be more precise in terms of calculating this pooled variance. You kind of see the rationale behind this. All right. So my final formula for my independent sample t-test. It'll be mean 1 minus mean 2 minus the difference, expected difference in my population values. That's going to cancel out to 0, right? So we just end up with mean 1 minus mean 2 over the standard error, the sample differences, right? Which is going to be my pooled variance, which I calculated here, divided by the one sample, plus the pooled variance divided by the size of my second sample. And then my degrees of freedom are sample 1 plus sample 2 minus 2. Again, I'm calculating, so going back to that degrees of freedom discussion that we had, I'm calculating 2 variance estimates. So I've got I lose a degree of freedom in sample 1, lose a degree of freedom in sample 2. So that's where I've dropped 2 degrees of freedom. Okay. Again, we talked about this a little bit. Why are we interested in knowing the degrees of freedom? and reporting degrees of freedom? Johnny?
Well, we said that degrees of freedom was like, the number of points that are like free to move or like vary, if you will, without impacting.
What does my degrees of freedom tell me from a practical standpoint about my sample? The size, right? We got some Scooby-Doo business in here, right? If there's funny stuff going on with, so like I lost some people or I didn't, right? And so like, if the degrees of freedom right there, it makes it very clear, right? Because I know what the degrees of freedom correspond to. If I'm looking at individual tests and degrees of freedom start jumping around and yeah, you do some sleuthing here, right? Just to go through and figure out what people are up to. But you know, if we start
I can tell I was. You did back yourself up at it.
I do know, Mr. T scared me, I do that. All right, so if you're thinking about, our effect size for an independent sample t-test, okay? Couple of different ways we can go. With our single sample t-test, there was really kind of only one option we had. Here, we've got a couple of different metrics. We could look at the raw difference between the two, scores. And again, let's say, Lindsay, you're doing, like saying, looking at weight across one group and another group. I know what weight is and I know how that relates to human beings. And so just a raw difference kind of tells me, I can start to make inferences about what that means in terms from a practical standpoint, right? Or most of the time we're working with scales that don't have any intrinsic value. So again, something like a standardized coefficient like a Cohen's d can start to be useful, okay? So Cohen's d, just like before, it's going to be my mean 1 minus mean 2 over some estimate of my standard deviation. Problem is, what standard deviation do we use? Because now we have more samples, right? So we've got more options. One option is going to be what we traditionally would call a Glasses delta, okay? Glasses delta, we're taking the deviation of mean 1 and 2, and we're dividing it by the standard deviation of some control group, okay? This is a nice option if you're comparing against some control that has some, so like just, this is where things are at baseline, right? This is just kind of where people are at in terms of stuff. Let's say you're, Mandy, running a study and you want to look, you've got people who were primed with just some neutral thing and like it's a random color bars or something like that that doesn't have anything going on. And then you have people getting things that should sort of maybe trigger some sort of handicapping or bias or something along those lines. Any group out group, something that should trigger that, right? Here, maybe what I do is I take the standard deviation and whatever I'm measuring, maybe I just take the standard deviation of the control group, because I assume this represents variability of sort of whatever I'm measuring of people just sort of in general, right? So if you've got a nice control group, a meaningful control group, Glasses delta is a nice metric, because what you can do is say, so we're seeing about a half a standard deviation increase in response to this manipulation relative to variability that we would just expect in the general population, right? That baseline or that control standard deviation gives us a nice kind of a meaningful interpretable metric. Okay? But sometimes we don't have a good control group. Sometimes we're comparing across things that just, I've got two comparisons that I'm sort of looking at, condition 1 and condition 2, and they're both active manipulations. Either one of them is a good like reference group. And so what I might do there is just take my pooled standard deviation, okay? And what I'm saying is this is just sort of taking essentially the pooled variability across my two groups. We're just kind of averaging it all out. And same type of thing, we still got the deviation score here. My standardizer now is just a pooled variance estimate. And you'll see this referred to as Hedges G sometimes, okay? In SPSS, if they call it Cohen's D, it's what it is. Cohen's formula is just mean 1 minus mean 2 over standard deviation. Cohen didn't specify what standard deviation. Cohen's like, well, I'm assuming the population variances are equal, so it doesn't matter, right? But when it actually comes down to brass tacks calculating this, which standard deviation are you going to want to use? Which that? Well, if I'm just wanting my effect size to be larger, Yeah, which I've got a one sample with a standard deviation of 3 and another one with a standard deviation of 2. Which one's gonna give me the larger effect size? 2, right? And so Cohen would say, in theory, it doesn't matter because the assumption is that the variance is equal across both of them, but when it comes down to it, I have to choose a number, right? So this is a theoretical thing, so make sure you circle that. This is like, because S is ambiguous. What we need to do is choose our standardizer, right? So we've got glasses delta, we've got hedges G. The thing that with hedges G is that we know that this is a biased estimate. What happens is, again, when we've got very small samples, what happens to our variable? What are we concerned about in terms of estimation of our variability with small samples? Yeah, small sample, we're worried about it's an underestimation of the variability, because I've only got like 10 people in my sample, so I'm not capturing the extremes. I'm probably just getting the middle, right? And if I've underestimated the variability in my population, hey, what happens to this? If my standard deviation value is too small, what happens to my G?
Are you asking if like the number, like how the number changes?
Yeah, how does this change if this is too small?
It's gonna.
What's that?
Increase or decrease?
Whether or not if this number is smaller than it should be, what's gonna happen to G? Mathematically.
You divide something by a small number.
Oh, okay, it's gonna decrease or increase. I don't
Increase.
know.
No, but like, I mean,
It's hard for me not to see it.
I know, but sort of just thinking about, sort of being comfortable with these ratios and going through, like, if this is too small, it's gonna make my G too large, right? And so this is a problem traditionally within experimental research where we're working with small samples. The concern being my effect size, even if I am calculating it, it's gonna be too big. Because if I'm using small samples, what's happening is I'm underestimating the variability of whatever I'm looking at. And if that's too small, it's gonna make my effect size too high. And then it's gonna make people think that I've got more of an effect than there probably actually is. And so what we see is we've got a correction to this, a small sample correction. If I look at here, the bias or sort of the effect on my hedges G with increasing degrees of freedom, we see that starts to sort of narrow out, right? So if I'm concerned about small sample bias and the inflating effect on my effect size, what I can do is add this correction factor. All we're doing is we're just calculating G like we did before, right? But then what we're doing is we're just multiplying that by 1 minus 3 over 4 times sample 1 plus sample 2 minus 2 minus 1. And I don't know why that works. It does. I haven't bothered to look at the math, and it was probably beyond me anyway, right? But no one said that it's wrong, so I'm assuming that people smarter than me have gone through and said that's an A-OK thing to do. But what happens, Jalen, as my sample size starts to increase and increase and increase and increase, you get bigger and bigger and bigger, what happens to this whole piece of that equation? As I start to divide 3 by larger and larger and larger numbers, what happens to that?
Smaller and smaller.
It gets smaller and smaller and smaller, and so then this whole correction factor starts to get closer and closer and closer to what? I take 1 minus an increasingly small value. It gets closer and closer to 1, right? And so if I multiply G by 1, then there is no correction factor, right? And so what we see with these is what we get is an adaptive correction that goes through as my sample sizes get larger and larger, the adjustment on my G gets sort of more modest, right? And so the question is, how small should my G be? How small should my sample be before I switch over? I don't know, right? It's sort of up to you, sort of depending on thinking about, like, am I concerned about overestimation of my effect size? Like, I don't know, this kind of gives you an example, just a general idea of kind of what happens with that. I don't know if you're really concerned. I mean, if you got like I've got a cell of 5 and 10, yeah, you should probably be using that. If I've got 20 and 25, I don't know, like you go through and you calculate them both ways and see like what's the actual difference. Does it make that much of a difference? Maybe, probably not, right? This is going to be a more conservative estimate, so you can make an argument that that's maybe okay. But at some point, you're just not gonna need, it's not gonna make a real practical difference on anything, so you don't need to worry about it, okay? When, in SPSS, when you're saying Hedges G, like this is the correction. The Cohen's D is what I was talking about before. Hedges G is just that correction on there, okay? Haley.
Yeah, so I guess I'm confused in terms of, so I know like the Cohen's, so we're talking about effect sizes
Yeah.
with all of these here. So I know the Cohen's D is kind of like this, like the standard, you know, what we use. So I guess in what circumstances, I don't understand why we would use anything like that, like the glass. Hedges G.
Okay. Cohen's D is a theoretical thing, right? So this is the formula for Cohen's D, but S is ambiguous, right? I have to make a decision on what S value I need to sort of calculate, right? Which is automatically going to drop me down into one of those. Now, nomenclature is different. You'll see people, like generally when you see someone reporting a Cohen's D, generally this is what they're doing. This is how they've calculated it. But this is important, and I think about like I try and do this for my papers, like I have in a footnote or something like that specifically what standardizer I'm using so people know which one I've gone through and selected and why, right? Because someone could report Cohen's D and it could be any of these, right? So it's important to go through and communicate what you've actually done, right? So this is kind of the gold, or not the gold standard. This is just kind of the default, right? Like, well, I've got two groups. One of them is not really a comparison group, so I'm just kind of taking the average variance across these two things, right? But I don't know, if I've got a really nice control condition, this is a nice way to go through and talk about things, because if I know I work in this area and I know what to expect in terms of variability in some sort of measure, this gives me a nice sort of kind of standard to sort of go through and think about. This is just the same thing as this, so we're just adding on a small correction factor, sort of knowing that we're gonna overestimate, that this effect size is gonna have a tendency to overestimate small samples, so we're just kind of tacking that on at the end. Okay. So again, this is where it gets tricky, right? Because what we need to do is think about, what am I doing? What am I studying? What are the implications? What's the potential for bias? What's the best for interpretation? And kind of use this to make a decision on which one of these metrics to use. Yeah.
So you said in SPSS, the corrected version, like that's just what they give us is the corrected version?
The Hedges.
Yeah, of Hedges, sorry.
Edges, yeah,
Yeah.
yeah. And this is what generally be like Cohen's D. Well, and look at the footnote on the thing. It'll tell you how
Oh.
they've gone through what they're using as a standardization. All right. From secondary analyses, right? Again, people will not always provide you an effect size, even if you want an effect size. Again, what we can do is kind of reverse engineer some stuff. If I've got test statistics and cell sizes, I can work backwards with that and get an effect size. If someone gives me, or I can go through and take a T statistic, 2 times T divided by the degrees of square root of degrees of freedom. This will give it to me too. Again, I want you to be using this because you have actual data available to you that you can go through and do this. But from secondary analysis, you can go through and reverse engineer stuff as well.
I have a question.
Yeah.
Should we always use like the Hedges?
No. I already know the answer because we always do anything? It's like, no, we should always never do anything. But what are you gonna say?
Should we most likely use the Hedges unbiased instead of the Hedges since that like inflates our value?
Only when our sample size is small, right? If I've got sort of reasonably sized samples, then the correction factor is going to be trivial. It's not going to be.
If it's reasonable, we'll use the glass one.
Well,
If it's normal, we'll use the glass.
well, this is for if I have a control condition, if I have a sort of a meaningful kind of control group, then sort of using this, right? So this starts to become maybe a more conceptual issue. Like, do I have in my independent sample t-test, do I have a group that just has intrinsic meaning in terms of something, or do both of my groups kind of have some sort of manipulation, and so there's no real good control group in there. Okay. So you come through, we can talk about it. Yeah. All right. What we've got here, so we've got researchers interested in school performance and students having watched Sesame Street, children, those who didn't. Scholastic performance in 10 high school students having viewed Sesame Street in childhood, compared with 10 students who had not. Students having watched the program had a mean grade of 93. Those with no exposure had a mean grade of 85. Okay, so again, a really small example. We've got 10 people. So one high school student who watched Sesame Street, 10 who didn't, and looking at grades and sort of wanting to test, like, do we see differences in terms of performance for people having early childhood exposure to educational programming, right? Same stuff as all we did before, right? We're just kind of going through and doing this for our independent sample T stuff, right? So again, this slide is just walking through and sort of calculations. Here's no Sesame Street, here's Sesame Street, sample size, mean, variance, right? So here, calculating our pooled variance, taking our pooled variance down in here to calculate our standard error, go through using that to calculate our confidence bounds. Right? So this is just same stuff we've been doing before. The only thing that's changed is calculating that standard error, and then just taking that pooled estimate right there as a difference. So grabbing that to go through and calculate our standard error. Here, calculating our effect sizes. So I've got students who calculated or sort of had watched Sesame Street, those who didn't. So depending on how I want to think about this, I can say, well, I'm going to calculate Hedges G because I just want to take the pooled variance and use that as a standardizer. I could calculate Glasses Delta, saying like, oh, hey, I've got a group of students who had no access to educational programming, and so that I want them to be my control group. And so if I do that, I'm using the standard deviation, my control, right? And so we see my effect size starts to change a little bit different in here. Here I would say I've got, it looks like the individuals, the students who had access to educational programming are scoring about 1.8 standard deviations higher than those without, sort of based on pooled variability across the two. Here I'm saying that those exposed to educational programming are scoring about 1.9 standard deviations above those who didn't, relative to just variability that we would expect in people without access to educational programming. Here, I got a sample size of 20. So I might say, well, I'm worried about small effect bias. And so I go in through and adding in my correction value, right? So I take 1.79 multiplied by my correction, now 1.17. So we see a small downward correction of that, right? It's not huge, but it's a little bit. My null hypothesis test, at this point it's easy, right? Here's I got my sort of difference that I see divided by my standard error. Gives me a test statistic of 4, p-value 0.0008, right? I go through, drop that in, there's my S value, there's my base factor, right? Remember that S values are always rounded to the nearest whole number, base factor bound down there. And so again, if I'm going through and writing this all up, mean grade of high school students expected exposed to Sesame Street, high school students not exposed to Sesame Street is equal in their respective populations. Okay. In notation, here's my confidence bound. Lindsay, can you give me an interpretation of this confidence bound? We ran through it pretty quick, but. What do we calculate? What's the numerator of my test statistic? This is going to be the difference in scores of people who grades of students who had access to educational programming and those who didn't, right? So what is my confidence bound going to tell me?
The overlap or
Kind of. Oh, so I've got my point estimate is the difference in scores, right? So what's the lower bound telling me here?
The lowest difference.
The lowest difference, and the up one
is the highest
the highest difference, right? So my based on my analyses, I'm saying that high school students exposed to educational programming have anywhere from a 3.8 to a 12.2 increase in final grade or sort of whatever as compared to those without programming. Here's my test statistics or my effect sizes, all of my statistics here. So here's my critical T with 18 degrees of freedom. Here's my actual test statistic p-value, right, in notation here. S value, base factor, and then down here at the bottom, right, sort of kind of tying this all together. We're saying high school students reporting exposure to Sesame Street in childhood demonstrated an 8-point increase in average grade as compared to high school students with no prior exposure to the program. Difference observed in these data is consistent with a 1.7 standard deviation increase in performance relative to the students with no Sesame Street exposure. Just dropping in my unbiased G because I've got a small sample here, right? Population difference compatible with data ranging from 3.8 to 12.2 percentage points in average grade, right? Despite the small sample available for our study or independent sample t-test, relatively strong evidence for greater academic performance in students exposed to Sesame Street, right? So basically evidence that against the mill in this study would be about roughly equivalent to 10 consecutive heads of a hypothesized fair coin. So Kate, if I said, hey, here, I've got a fair coin, I shot 10 heads in a row, you might start to seriously question whether that was real, right? We can say that upper bound for likelihood of the alternative relative to null is about 64.5, right? We say, although the methodology of the study requires additional scrutiny, current data suggests that exposure to educational programming could be associated with 2/5 to over a full letter grade increase in average exam scores, right? So again, with this, trying to get in how much, right? So because this starts to become important, like not just it's a different, how much different is it, right? So we're talking about an 8-point increase, so about 1.75 standard deviation. How precise, right? So what does our data support? Anywhere from about a 4 to about a 12-point increase. Evidence against the null hypotheses, right? We've got pretty strong. I mean, this is small. This is only a sample size of 20, right? But it's still, even with that, it's looking promising, right? So tying this all together, not a perfect study, right? And there's certainly a lot of other things that can start to go into whether or not someone was exposed to educational programming early on, right? So we would in no way say that for sure Sesame Street is making people perform better, but it's saying that there does appear to be some association there, and just trying to tie this in a way that is meaningful, talking about practical impact of this stuff. So again, just an example of trying to show you how you can start to pull this stuff together to make some interesting interpretations about what's going on, as opposed to just saying, oh yeah, there's an effect or there's not an effect. All right, we went through, covered that really quickly, but what we'll do when we meet next week is we'll go through, finish up the actual independent sample t-test, and then the paired sample stuff will go pretty quickly. So we're a week behind, but we've been in far worse places. I would much rather spend time and have you understand this than sort of rush through it, just so that we're on track with stuff. So sound good? Awesome. All right, thank you so much for bearing with me, and let me keep you a minute over, but let me know if you have any questions. Otherwise, thank you so much. We'll see you.
I think I'm gonna click back one slide.
Yeah.
Is there any way to like calculate using the lower bound to like say even if the like lowest,